They want us. All right. Thanks a lot for including the paper on the program. It's joint work with Thibaut Angron, who's a great grad student at Stanford, and Diego Consek, who's at Northwestern and also in the room today. The starting point of the paper is that economic growth and climate change are deeply linked. Much of economic growth has been and is still powered by fossil fuels. But as we burn fossil fuels, emissions accumulate in the atmosphere that warms the planet. And to the extent that it imposes economic losses on the world, climate damages may slow the very growth that has produced those emissions. Now, at the same time, despite this deep link, much of what we know about carbon policy relies on the assumption that warming will magically stabilize in the not too distant future. Now, there are reasons to doubt this assumption. There's still a lot of fossil fuels in the ground, and if we burn everything we know, we could warm the planet by 10 more degrees. And as a whole, the world is still far from having decarbonized its economy, despite sizable policy intervention in parts of the world. And so all of that suggests that it may be reasonable to assume that warming may actually continue for the foreseeable future. And so in this context, we want to ask the following questions. First, is sustained growth compatible with climate change, or will climate change crash the economy? And to the extent that there is a sustained growth, how does the interplay between growth and climate change the way we think about climate policy? And so we're going to answer these questions in the following way. First, we're going to develop the simplest framework in which we can analyze jointly growth and climate change. So we start from the neoclassical growth model. There's technological progress in there. Production requires energy. Energy leads to emissions. Emissions accumulate in the climate that warms the planet, leading to productivity losses. That's the classic carbon externality. Then we start with a positive analysis. And so we show that under some conditions, balanced growth is indeed compatible with continued climate change, but that climate change slows down the rate of economic growth. That's going to require some physical scaling laws to hold, as well as a log linear relationship between productivity losses from climate change and temperature. Now, the good news is that this log linear relationship is what people have estimated over and over again in the empirical literature. In the paper, we also discuss what happens when we depart from this log linear structure. Then we move on to the normative part of the analysis. And this is where the interplay between growth and climate change really comes alive. And so what we show is that it leads to two types of policy regimes that depend in particular on the magnitude of climate damages. So if climate damages are not too big, you're essentially in the traditional case. In that case, the planner selects the same long-run growth rate of the economy as the laissez-faire and only corrects the level of economic activity with a stable carbon price over time. When damages are above a threshold, in that case, something different happens. The social cost of carbon, which is the present value of future losses associated with emissions, can actually exceed the static marginal product of energy. The planner doesn't like that, and the way to restore this equality is to actually put a hard cap on the rate of warming, which is a more aggressive carbon policy than in the first case. So what's the upshot of moving more aggressively and capping the rate of warming is to achieve faster economic growth by limiting the accumulation of carbon and the escalation of damages. And you decentralize that with the rising carbon price over time. And then we put some numbers on this theory. So we're going to explore the full range of empirical estimates of climate damages, going from about 3% productivity losses per degree Celsius to the high end, which is 25% losses per degree Celsius. The first thing we show is that actually this second regime, this cap, binds not exactly at the lower end of the range, but not too far from the lower end of the range. So you don't need very large damages to actually make this cap bind and the second regime to occur when there is growth and climate change at the same time. And then we're going to look at the extremes. So at 3% productivity losses per degree Celsius, we find that the optimal policy achieves a 1% welfare gain. The cap doesn't bind, and the planner allows somewhere between 3 to 8 degrees Celsius of warming per century, depending on where you are exactly in the transition to the new BGP. So here you recover more or less the classic Nordhaus calculation. At the high end of the range, something different happens because the cap binds. And so the planner moves aggressively to cap warming at 0.4 degrees Celsius per century. The upshot of doing that is that you achieve nearly 1 percentage point higher growth in the long run by limiting the accumulation of climate damages. And so that results in a 26% welfare gain, accounting for the transition. And then we also show how these results change when you introduce backstop technology or look at nonlinear damages. Okay, so let me jump right into the theory. So the economic side of the model is going to be fairly standard. So households have time-separable preferences, CR utility, and talk. I'm going to focus on log. Production is Cobb-Douglas, requires capital, labor, and energy. The energy share psi is an important parameter, so keep that one in mind. And then productivity will have an exogenous component and an endogenous component. To produce energy, you have to extract it from the ground at an extraction cost chi-t that can be rising over time to capture fossil fuel scarcity as we extract more and more. The resource constraint is standard. You consume, you invest using output net of capital depreciation net of extraction costs. In the laissez-faire, all the markets are going to be competitive, and you have a standard budget constraint in that case. Okay, the climate side of the model is going to be a little more interesting. So when you use energy to produce, that leads to emissions EM. But we're going to allow for a sigma t in between, which is going to capture the carbon intensity of energy. And so if sigma t is falling over time, that's going to be capturing progress in renewables. And then these emissions enter carbon sinks. There are M of them, and so that's captured by the vector here. So think about the carbon sinks as being the atmosphere, the upper oceans, and the deep oceans. So emissions enter the atmosphere, ETM here, and then they slowly mix across the different sinks. So the matrix A encodes how carbon mixes into the oceans, and the vector big M here is simply the carbon content of every sink. Okay, then as carbon accumulates in the system, that leads to radiative forcing, so more energy retained in the atmosphere, FT, and so that relationship is in logs, actually. And so that's an important scaling law in physics called Arrhenius' law, dates back to quite a while. That's going to be important for balanced growth to arise. Okay, H controls the climate sensitivity. It's a matrix that tells you how much more carbon generates a radiative forcing. And then finally, the radiative forcing increases temperature according to this law of motion for temperature in all of these pieces of the Earth that we're modeling, according to the matrices N and B that encode some physical constants. So for instance, how much energy is exchanged between the oceans and the atmosphere and how much energy is lost to outer space. And finally, the climate matters because it feeds back into economic activity. So we're going to posit a pretty standard damage function here saying that total productivity is going to have an exogenous component Z bar that rises exogenously over time. That's the engine of growth. And then an endogenous component here that reflects climate damages. So it's log linear. As temperatures rise above their pre-industrial equilibrium, that's going to lower productivity according to the vector of coefficients zeta. So you can think of it as just one number, if you will, just one number that loads on the atmospheric temperature. And so zeta is going to play an important role as well. Okay, then the laissez-faire is completely standard. Households maximize present value of utility, firms maximize profits. Nobody internalizes how emissions feed into the carbon cycle. And so the key optimality condition here is simply the energy demand that states that the marginal product of energy is equal to the extraction cost. Okay. The planner solves a related problem, but of course internalizes that as you use up more energy to produce, these emissions are going to, in the long run, lower productivity through climate damages. And so the only condition that differs here is the optimal energy use by the planner. So there, the marginal product of energy for the planner has to be equal to the extraction cost plus the shadow value of those emissions. And that's, of course, the well-known social cost of carbon, tau t, which is a forward-looking object that is the present value of all future losses associated with emitting 1 ton of carbon. Okay, and so now the name of the game is to figure out how the laissez-faire looks. That's going to be our first result. And then how the planner solution looks. That's going to be our second result. To state those results, I'm going to define a few objects. The first one is the growth rate of technology. So that's going to be the growth rate of the exogenous component Z bar of productivity. For all the other variables, I'm going to call Gx the growth rate of X, except for sigma, where I'm going to put a minus sign so that positive G sigma means progress in renewables. Then we're going to define the rescaled energy share, which is just psi divided by the labor share. So we're going to call that pi. And then an important object is growth in carbon savings, omega. What is it? It's how much the economy is saving on carbon on its own absent policy intervention. So it's going to depend on the growth rate in renewables, if you will, G sigma, and the growth rate in the extraction cost. That's going to make it less interesting to use more energy if that's high. And then finally, we need 3 long-run elasticities to the carbon stock. The first one is the full climate sensitivity theta. That's going to depend on the diagonal of the H matrix that we've seen before, adjusted for some physical constant. Okay, so theta tells you if I double the carbon stock, how much does a temperature change in the long run? And then we're going to have 2 measures of damages, undiscounted damages, big delta, which is just our damage vector zeta interacted with the climate sensitivity. So that's the long run elasticity of climate damages to the carbon stock, and then we have a discounted version of it, delta bar. Okay, so now we're ready to state our first result. The first result is that there's a unique constant growth path, which is also a BGP here, that can take one of two forms. In the first case, technological progress is less than growth in carbon savings. Okay, in that case, energy demand is rising more slowly than progress in renewables. And so in that case, emissions are falling exponentially, temperatures stabilize on their own, and so there's no interaction in the long run between growth and climate change. So that's the case in which asymptotically in this model, there is something like a backstop technology whereby emissions are just falling on their own. The more interesting case is the second case, which is also the empirically relevant one. If productivity grows faster than growth in carbon savings, actually emissions are growing exponentially over time. With exponential emissions growth, then the carbon stock is growing exponentially. Because of Arrhenius law, temperatures are rising linearly over time, and because the damage function is log linear, that exactly balances with a technological progress, and so you also have exponential growth in output. Now, the key, of course, here is that the growth rate of output depends on technological progress and these other objects, but is scaled down by the magnitude of climate damages. And so the higher the damages, the slower economic growth. Okay, so that's our first result. You can have balanced growth with climate change under the conditions that we've laid out. Now, of course, now the next question is like, does it change the way we think about optimal carbon policy? So that's going to be our second result. It's a little more involved, so I'm going to state it first, and then I'll show you the intuition in a special case. So our result is as follows. There exists a cap on the growth rate of emissions, GM bar, and we call it a cap because it's independent from the rate of technological progress. So no matter how fast the economy wants to grow in the laissez-faire, the value of this cap is always going to be the same. And so this cap is as follows. We again have two cases. If technological progress is less than carbon savings plus a little bit of wiggle room that depends on damages, then you're back in the sort of standard case in which here the planner is going to select the same long-run growth rate of output as the laissez-faire, is only going to affect the level of economic activity with a stable carbon price over time. Okay, so that case arises when either temperatures stabilize on their own or when they rise but moderately over time. Again, the interesting case is the second one in which growth in technological progress is high enough relative to growth in carbon savings. In that case, something different happens. The planner says, no, I don't want all these climate damages going forward. I'm going to put the brakes and I'm going to do something different than in the first case. In particular, the planner is going to impose a cap on the rate of emissions growth. So the planner is going to always choose GM bar as the growth rate of emissions, which is strictly less than the growth rate in the laissez-faire. As a result, the planner is going to achieve a slower growth rate of temperature than in the laissez-faire. What's the upshot of doing that is that you can achieve a higher growth rate of output than in the laissez-faire. How can you decentralize that? By using a rising carbon price over time. Okay, so this result might seem a bit surprising at first, so let me walk you through the intuition. The intuition is easiest to see in a one-dimensional climate system. So let's take just one layer, one sink, and growing emissions over time. So in that case, following the logic that's not unlike the one in Golosov et al. 2014, you can show that the social cost of carbon takes this very simple form. So the social cost of carbon is increasing in climate damages, delta bar. That makes sense. It's also proportional to the marginal product of energy here, psi y over E. But importantly, there's this extra term here that enters and that depends on economic growth. So what's the logic here? So when emissions are growing very fast over time, when GM is positive, in that case, the carbon stock in the future is very large relative to today's emissions. And so that means that damages are going to be large in the future. And so the social cost of carbon relative to today's marginal product of energy is large. What does that matter? Well, stick this back into the planner's optimality condition. You get that the marginal product of energy is equal to the extraction cost plus our social cost of carbon, which is something times the marginal product of energy. Now, of course, if this something here in the middle is too big, this first order condition can never hold. Of course, that would violate optimality. And so what does the planner do if that object in the middle is very large? Well, the planner says, well, stop. I never want to go above some growth rate of emissions, GM bar. And so you can solve for GM bar using this condition, and you arrive at the following very simple formula that the cap on the growth rate of emissions is equal to, is increasing in the energy share pie. That makes sense. If the economy is very reliant on energy, you're not going to cap emissions too aggressively, and is decreasing in climate damages delta bar. If damages are high, you're going to cap more aggressively. Okay, let me show it to you graphically. So panel A shows you the growth rate of emissions as a function of our damage coefficient as zeta. So initially, before the cap binds, the planner and the laissez-faire choose the same growth rate of emissions. When damages are high enough, there's the regime switch, in which case then the planner chooses to cap emissions much more abruptly than what happens in the laissez-faire. What's the upshot of doing that? Well, you see that in panel B, which is the cross-sectional plot of the growth rate of output as a function of the damage coefficient. So initially, they're both falling at the same rate, but once you switch regime, the planner actually achieves a near constant growth rate of output, even at high damage coefficients, whereas in the laissez-faire, you have this continued decline in the growth rate of output as damages arise. Okay. So in the paper, we go through lots of extensions of this baseline framework. You can add population growth, CRA preferences, you can change the way you pay the extraction cost. You can have dynamic management of exhaustible resources a la hoteling. You can endogenize the growth rate of the economy through creative destruction. You can endogenize progress in renewables through creative destructions. And you can look at what happens when the damage function deviates from log linearity. We worked all of that out, and I'm happy to talk about it in the Q&A. I'm also going to skip how we estimate this model and go straight to the quantitative results. So we're going to explore the full range of damage coefficients that's been emphasized in the empirical literature. So let me start at kind of a lower value, say maybe 3% productivity losses per degree Celsius. So in that case, the planner selects the same long-run growth rate as the decentralized equilibrium. So the blue line is the laissez-faire, and the red line is the planner. And so you can see that these two lines nearly coincide up to 2200, with a little bit of a level effect here that you see on consumption. This is output and this is consumption. This is not a different growth rate here in the dash red. That's the level effect that the planner achieves by slowing down emissions still along the transition. Panel C shows you the temperature path under the laissez-faire and the planner. And so you see that the planner does slow down the rise in temperature by imposing a carbon tax. But in the very long run, the growth rate of temperature is the same in the planner's allocation and in the laissez-faire. And so it's initially 3 degrees per century. And then as as oceans catch up, actually, the planner tolerates 8 degrees of warming per century in this particular calibration. Now you can go at the opposite extreme. When damages are high, 25% productivity losses per degree Celsius, what happens? Well, in that case, the cap binds. And so the planner selects a different growth path as the laissez-faire. And so you can see it here for output and consumption. The planner is putting the economy on a different growth path than in the laissez-faire. And so by the end of the 21st century, which is in quite a while, consumption is about twice as large in the planner's allocation than it is in the decentralized equilibrium. Why? Because annual growth is larger by about 0.8 percentage points. Okay. Now, of course, it doesn't come for free. There are some losses, early on because you're kind of cutting abruptly on energy use, and so that comes at a cost in the short run. Now, you're cutting abruptly so much that you're actually capping the rate of warming at about 0.4 degrees Celsius per century, and so by the end of the 21st century, that's a large gap in warming across these two allocations. Okay, so now let me show you what happens in the full cross-section of damages. So now we're going to put cumulative damages on the x-axis, so the value of the damage coefficient on the x-axis once more, and then on the y-axis here we have the long-run rate of warming. And so this is just to show you that the conclusion that the cap binds and binds in a meaningful way doesn't really rely on going to one extreme or the other of the damage distribution. And so this is the BGP rate of warming. So this is in the very long run. And so you can see that the cap binds, that's the vertical black line, is just above our lower value for the damage estimates. But as soon as you go a little bit to the right, if you were looking at, say, 6% productivity losses per degree Celsius or 10%, you would already be capping the rate of warming in the efficient allocation by quite a bit. Not quite as much as if you go to the high end, but this slope here is very steep. And then finally, the final figure I would like to show you is welfare gains as a function of the damage coefficient. So again, damage coefficient on the x-axis here and the y-axis, welfare gains in consumption equivalent, inclusive of the transition. And so you see that at more moderate values of damages, you achieve 1 to 2% welfare gains from implementing the optimal policy. There's some convexity in the welfare gains here. And so if you move to the right of the range, in that case, you achieve 25 to 26% welfare gains, in part because you're capping the rate of warming more aggressively. All right, that's all I have. Thank you very much. And I'm very much looking forward to your discussion, Nishan.
All right, thanks so much for inviting me to discuss this. Just so people can focus on my content, I will say for 1 second that I'm wearing athletic shorts because my khakis do not fit over my boot. Uh, and I'm wearing a boot because the Harvard undergrads couldn't guard me at pickup basketball and they had to take my ankles out. But the revenge in 4 months is going to be epic. Uh, all right. Okay. I'm super excited to talk about this paper. I have so many things to say. I love talking about climate change and growth. Okay. So the first thing I want to do is spend several slides just driving home why this is like such an important research question that's like totally annoyingly absent from the literature. So I'm just going to take a bunch of quotes. I think actually these quotes might not be in the newest version of the paper, but they were in the version that I discussed or that I read. I'm just going to take a bunch of quotes and show you guys the data on why this is so important. Okay, so these guys are telling you, okay, known fossil fuel reserves, 10 C of warming. We know there's 10 C of warming in the Earth, and also what this graph from this Covert, Greenstone, and Knittel paper shows is reserves are growing over time. We've been finding fossil fuels faster than we've been using them. And so this whole idea of fossil fuels is like a hoteling resource that's exhaustible. It's basically like totally fake in the data. You should think of it as like a totally inexhaustible resource, roughly speaking. There's like, we could burn the earth to a crisp with the amount of fossil fuels we have is I think like the model you should have in your head. Also, this whole paper is about emissions growth. We hear a lot about like the renewables revolution. I just want you to have like a picture in your mind of that little sliver of orange right there. That's the renewables revolution over the last few years. This is the fossil fuels. That's oil, that's coal, that's gas. They're still growing. Also, the Earth's climate doesn't care about the proportion that are renewables. It cares about the total emissions from the total fossil fuels. It's still growing year by year. And so this idea, I'm actually going to go a little out of order in the slides, but this idea that's embedded in like every other climate economy long run paper that emissions just stop after 2100, it's like totally annoying to me. Like we've been emitting forever. We have infinite fossil fuels. Like maybe the renewables revolution means that we stop emitting in 2100, but I think actually it's just like, it's like mathematically annoying and quantitatively difficult to deal with emissions after 2100. And so people just don't. This is one example of like the path of emissions from an excellent recent paper about population growth and climate change. And you can see like after 2100, like the emissions are just gone and we just assume them away. But that's my assumption. I don't think that's like for a good reason. And then furthermore, these temperatures that people talk about in 2100 in certain emission scenarios, like everyone's talking about 3C, 2.5C, 3.5C. If you look at the probability distributions, this is in like a pretty high, fairly high emission scenario. This is the probability distribution of temperature by year. And again, this is an emission scenario that bakes in that emissions stop shortly after 2100. And so this is like, even if they stop after 2100, we're talking about in 2100, like sure, 3C, 3.5C is like the median of the distribution, but this is like the tails go out to like 5 or 6C and they're not like that thin. Then you look out further centuries and like, yeah, like 5, 6C, 8C, it's like totally possible. Like nobody's sitting here looking at these PDFs, but you just like, I want these PDFs to be burned in people's minds. Like this is why it's super important to be writing a paper about the very long run where emissions continue to be growing. So I think it's just like an incredibly exciting research question. Now, just to say a little bit more about the physics of how the climate system would respond to these like ever-growing emissions, the model you should have in mind, Adrian explained all this already, but just kind of like to repeat it in my own words, which is always helpful for my understanding. Basically, temperature is going to double. A doubling of CO2 concentrations in the atmosphere is going to lead to a constant change in temperature. So if you double CO2, you get a 3%, about a 3-degree increase. This is like the key climate sensitivity parameter that in climate science everyone is arguing about, like how sensitive is the climate to temperature change. But the important thing is if a doubling leads to a constant change, that means that an exponential growth in emissions is going to lead to a linear growth in temperature. That's what's embedded in their model. Okay, that makes sense. And so the paper, I think, it makes a reasonable assumption that emissions keep growing. So the stock grows exponentially, temperature rises linearly. So it's worth saying if we were able to bend the emissions curve and make emissions constant over time, temperature would keep growing forever. Constant emissions is not a steady state for the world's climate. It would grow concavely, temperature would rise concavely because emissions the concentration would be rising linearly. in that scenario. But for warming to ever stop, that would only happen at net zero. So only if we get to zero emissions at some point centuries from now does warming ever stop, which I'll say more about in a couple slides. Okay. And so this paper is kind of taking this seriously, thinking about, okay, what if we get to 7C, 8C, et cetera. And so to me, the biggest contribution of this paper in kind of like a long run, how do we think about climate change sense, is just everyone's been ignoring this, and it's like probably we shouldn't ignore this. Is my view. Okay. Now let me talk a little about the level and the growth effects. So I think they make a really important subtle point here, which is like in the literature, there's this whole literature, my own papers are in it a little bit, of is climate change likely to manifest as a level effect or a growth effect? Now in this literature, everyone's having this debate. Everyone's considering a permanent level change in temperature and saying, suppose temperature goes up 3 degrees forever. Is that going to be a level effect? Is that going to be a growth effect? That's what all these papers are arguing about. And now what these guys are doing is making the really good point that's like, well, actually, a permanent level change in temperature is literally not what's happening. The world is getting progressively warmer and warmer and warmer. And so their point is like, okay, even if a permanent level shift in temperature is a level effect, if temperature is trending, then that means you're getting a growth effect out of that. And so that's what's baked into their model. I think it's a really excellent point that is kind of weirdly overlooked in these other papers, including weirdly overlooked by me. Okay, so that's kind of like the core thing that's going on of how temperature is affecting growth. Now, let me get into these two regimes. And this is kind of like, gets towards like where I would like to see the paper. Maybe it's just that I have like a different prior of what the right research question is about their motivation. But this is kind of where I'll have something to say about what their two regimes like do and do not do. Okay. So the planner has the low damage regime and the high damage regime. And the difference here is like in the low damage regime, the planner is going to reduce the level of emissions and the carbon price is going to be constant as a share of energy extraction. In the high damage regime, the carbon price is going to rise and the planner is going to cap the growth rate of emissions. And then you have this like intertemporal dynamic that Adrian was explaining where the planner is going to make a sacrifice in growth at first, accept lower growth, but then you get higher growth in the longer run because you have this reduction of damages. So that's what the two regimes do. But when I was kind of reading the introduction, there's a number of things that I thought the two regimes were going to do that they don't do. And so I'm going to say what the two regimes do not do as well. Okay, and so why does the switch happen? It's because at some point the planner, why do you switch regimes? It's basically when the present value of all the future damages from the marginal unit of emissions is going to outweigh the output, the marginal product it would create now. At that point, you want to reduce the growth rate of emissions, so that stops being true. But so that's what's different across regimes. But what's not different across regimes is that there is this permanent growth effect in both regimes. So in the low damage regime, there's still a permanent growth effect of climate change. When Adrian said the laissez-faire and the planner's solution has the same growth rate, that's the same growth rate because the planner accepts this climate growth effect. So there is a climate growth effect in both regimes. It's only the rate of that growth effect that's different. And importantly, neither regime is going to stabilize temperature here. And so you're still going to get forever warming, whichever decision the planner makes in either of these cases. And I think that's kind of one thing I want to focus on in my first comment. Okay, and so what's happening here is emissions in the laissez-faire or in the low damage planners regime are growing forever. In the high damage regime, emissions are also growing forever, just slower. And so you get like this permanently increasing temperature. The cap on temperature is a cap on temperature growth. And so there's like a part of the paper where, at least in the draft I read, there's a line that says, we get, a cap that's like 1.4 C by 2100, which is like the language of the Paris Agreement. And I felt like that was sort of like going away from where the paper had this grand vision. The grand vision is like these temperature targets in a static timeline by 2100 are actually like not capturing the dynamics of the problem in the long run. So the planner solution here is giving you like this number that, conveniently in the quantification lands at like something that maps well to the policy debate. But this is actually like a paper that's saying that whole way of thinking about it is kind of wrong. Okay. And so just to drive that home a little further, and it'll bring me to my next point, in both regimes, you're going to have this permanent growth in temperature. So the red line is like the laissez-faire, it depends a little on the quantification. You're getting like 3C, Adrian was saying, per century. It could be a little higher than that in the longer run, depending on the ocean dynamics, et cetera. The blue line is like in the high damage regime, the optimal temperature growth. But basically, like they're saying, if you think damages are bad, you're going to get this slope of temperature from the planner. If you think damages are less bad, then you're going to get some other slope in between here. But like temperature is rising forever, regardless. And so this like change of regimes is still like you have this constant long run temperature change. Okay, and so basically, this slide's maybe a little repeating things I've already said out loud. There's a growth effect in both regimes. At the low regime and the high regime, the temperature is rising forever. And so what matters is the slope of temperature change and the slope of emissions growth. That's what the planner is controlling. But it's basically coming down to how bad our damage is. And so we have like all this infrastructure about the very long run and these really good points. But now the paper's kind of like coming back to the old debate, which like everyone's debating in all of the papers about optimal climate policy, which is like damages are really bad. You control emissions more and it goes slower and so forth. And so as a result of that, the quantification sort of comes back to this debate of like whose damages should we be using, which I would sort of prefer not to talk about because I'm a little bored of like our previous papers. But since that matters a lot for the quantification, Pete's shaking his head. Sorry, Pete. Okay, but my point is I want to talk about like this grand vision stuff of 2200, but really to get at the quantification here, we need to talk about like whose damage estimates do you believe? And the only thing people ask me more than what happened to your foot is like, what do you think about the damage estimates in Adrian Diego's previous paper versus your estimates in Valerie and Pete, in the paper with Valerie and Pete? So I'll chat about that for a minute. Since I already told you about my foot, and those are the only two things that people ask me. Okay, so just to like put on a bar graph how different the different estimates are in the literature, this is like kind of the classic stuff, like the Barrage and Nordhaus is the most recent DICE model damage estimates. And this is, it's all kind of like roughly 3 to 4C by 2100. It's not exactly apples to apples, but it's pretty close. So this is like a bunch of people's estimates who are estimating level effects. In my paper with Valerie and Pete, we're saying there's likely to be persistent growth effects that don't last forever from a permanent level change in temperature. We get these damage estimates that are like 4 or 5 times larger. That's in contrast to a paper that came before us by Burke, Shang, and Miguel that had permanent growth effects from a level change in temperature. That's twice as big as our estimates, 3 times as big, depending on which specification you choose. And then this is the set of estimates from the global temperature time series estimates in Adrian Diego's previous paper. So I kind of just want like in people's minds, like just how different these damage estimates are. And so like, obviously, if you plug in these different sets of damage estimates into a planner's problem, you're going to get wildly different slopes. So I'll just talk for like maybe a minute or two before making other points about like, everyone believes their own papers. Why do I believe my paper? Okay. And then a kind of side point, which I think actually they handled in one of the extensions that might not have been in the draft I saw, is they say damages are log linear, but in our paper, they're like highly nonlinear and they affect hot countries much more. And that's actually, I think, quite important. I'll say more about that in a minute. I think I have like 7 minutes left. Okay, so I'm just going to comment a little on like how we might anchor the damage estimates in these previous papers to microdata and why it might be reasonable to have certain priors. Okay, so this is like the impulse response functions of GDP to like a 1 degree shock in temperature in hot countries, medium countries, cold countries in my paper with Valerie and Pete. And basically, the only thing I'll say here, Adrian and Diego have heard me say this before in previous discussions, is if you kind of add up the micro estimates, you sort of get exactly this number. Like if you add up how bad do we think temperature change is in agriculture and manufacturing, you kind of get the contemporaneous effect. So if you're trying to anchor the macro estimates, which have like all the shortcomings of macro estimates, to micro estimates, which we know much more about, the shortcoming here is we don't really know why the effects are so persistent, but we can explain like the contemporaneous effect pretty well with microdata. And just for some examples of the microdata, this is like from my previous paper where I estimated like the effects of extreme temperatures on factory productivity around the world. Another paper of mine where like we do the estimates for agricultural yields around the world. There's like 55 countries of microdata. We know a ton about different crops and all the different weather extremes they face. So basically, like if you think that microdata is where we can learn the most, we can anchor that set of estimates pretty well to microdata and understand where they come from. I think that's a little bit, in my view, in contrast to like the famous impulse response function from Adrian Diego's previous paper. And so they say in this paper, the global time series estimates are 7 times larger because they capture these damages of extreme weather like rain, winds, droughts, floods, storms, et cetera. Thanks. And I think that's like totally plausible, but I think there's still a gap in the literature where we get micro estimates that are like giving us magnitudes that are this big. And so just to compare this, so this is like a 1 degree shock in global temperature. It's something like 14, 15, 17, 18% at the peak decline in GDP in these global time series estimates. And that's like, to put some context on it, this is like the most recent paper on by people who study this really thoroughly on the impact of cyclones on GDP per capita. And you can see like a category 3 storm that hits 1% of a country's land area is knocking down GDP at the peak over the 10-year horizon by like 0.1%. And this is the density of how much of the land area is hit by different storms. It's like, 15, 20% of the country is hit by a storm. That's like 1 or 2% of GDP. The storms are really bad. So basically, like, we don't really know where this number comes from, is my view. And so that's why you might want to anchor to something that we can like know where it comes from better. Okay, so that was my only comment on that. I have a couple more things to say. One is that I think the nonlinearity actually matters a ton here, and there's a lot you lose when you do a quantification that's like a global representative agent for climate change especially. So just to put that point here, this is like the quote unquote low damage regime, which is basically my estimates with Valerie and Pete plugged into this 7.5 degree C world in 2200. And you can see like at 7.5 C, we're saying like GDP is going to fall by like 70%. In most poorer parts of the world. Obviously, there's all sorts of other like conflict, migration, tipping points, other things we're not covering. And also like at 7.5 C, I think we're just totally guessing. It's like so far outside the range of human existence that like, why should we believe any empirical estimates? There's a paper published in Nature that's basically like 55 million years ago, it was 6 degrees hotter than it is now. And there were literally alligators and palm trees at literally the North Pole. And so, projecting empirically what's happening when there's alligators at the North Pole, I don't think we should be really like anchoring too hard to that. And so my view is like, the planner accepts like 6C in the low damage regime in this paper, but to me, it's like the planner would have to be like crazy. Like literally, how crazy would the planner have to be to accept this world? There's alligators at the North Pole. And so I think part of that is like incorporating a whole world and the heterogeneity across space is, I think, really important. And, obviously you can't handle all this in this paper, but like in this 6C, 7C, 8C world, I think a lot of the interesting questions are if maybe beyond economics at all, but certainly like beyond things where learning from the historical data is that interesting. Okay, and then this is kind of an aside, but I sort of have, I'm fascinated by the fact that like carbon prices are highest in the least vulnerable countries to climate change. And so that causes me to question the extent to which like this how bad are damages literature is really that influential for policy. My view, if I'm being totally honest, I guess this is on YouTube, so maybe I shouldn't say this out loud, but like, I think the policy people are I think we're having this discussion in really good faith. And I think the policy people are mostly reading this in totally bad faith. Like people have their pre-existing ideology about how bad climate change is, and they like cherry pick which set of studies show that. And so I sort of want to move beyond the like how bad are damages in this literature. Okay, so last thing, I think I have 1 minute left. I figured since I'm like up here wearing athletic shorts, I might as well have a slide that's like my hot takes about climate change. And this really gets at one of my like really important takes about climate change. So I have a few of these. I think in rich countries, it's probably not as bad in our lifetimes as the newspapers suggest. In poor countries, it's probably a lot worse. It's like a really first order issue for development. People are not talking enough about the uncertainty and tail risks, which is closely related to what Diego and Adrian and Thibault are doing in this paper, because like a lot of those are getting out to those 7, 8C worlds. And then also I think the very long run is just underappreciated. People think that fossil fuels are finite and that the world ends in 2100, and those things are not true. And I think it's really important that we have a paper about that. But that being said, conditional on writing a paper about the very long run, I think there's all of these aspects of the question, like, is it even right to think about slopes if we're thinking about the very long run? Should we be thinking about like how to set a target for cumulative carbon? You know, the climate people talk about dates for net zero. I think there's so many aspects to this question once you open up this box of post 2100 and the very long run and infinite carbon. And so, you know, if I were writing this paper, I would have gone more in the direction of like, there's so many qualitative things we haven't talked about the extremely long run. And so maybe there's some way to push in that direction. It's kind of my closing. Thanks again for inviting me.
Start well. Yes. Super interesting paper and discussion. I was thinking about the emission intensity and endogenizing that. Of course, you need to keep the model simple, but if I look at catastrophic scenarios, it's like coal is the really big thing. Coal is dead with like a 5 cent per kilowatt hour versus nuclear, and nuclear is extremely substitutable with coal. So that means that maybe you're just exaggerating a lot the cost of mitigating this. That if you would go to the engineering estimates, sort of see like how much would die at different carbon taxes, I suspect it's much more substitutable than you make it. You even have exogenous emission intensity on your thing. So we can sort of fight about the damages, but I think that I agree with the challenge, just stop them. And I think it's important also to have a paper that gives a realistic prospect of how expensive that will be.
Yeah, thanks. So, you know, as Ishan was showing in his motivation graph, you know, you see all consumption of all fossil fuels is still rising. So that may change in the near future, of course. But so far, we're still emitting more and more every year. To your other point, like we do endogenize carbon intensity. So we have this extension where we have creative destruction in the energy sector. And so you can switch between fossil fuels and renewables in that sector. But then, of course, it matters a lot what the elasticity of substitution is there. And so we don't have much to add on that front.
This is a related question, but can you give the intuition as to why a planner whose discount rate converges to zero would not go to net zero emissions? Although I suspect it has something to do with the elasticity of substitution, you die if you go to zero emissions with Cobb-Douglas.
Could I put back the slides? No, thanks.
I guess just to add to that, would an elasticity of substitution of 1 plus epsilon then mean that we someday go to net zero if we're sufficiently patient?
So in the first part of your question, I think, you know, this formula answers it exactly. If rho is zero, the GM bar is zero. And so you do go to net zero. So your intuition is exactly right that if you're infinitely patient, you don't want any emissions at all, because otherwise, you know, these very large damages in the future are just too costly. On the other question, yes. So the elasticity of substitution slightly above 1. So that's hard for us to deal with. Like in the theory, I would love to have something concrete to say. My guess is, you know, if it's not too far away from 1, you know, numerically, you would get something pretty close for the next 100 years, maybe 150 years. And then in the very long run, you know, the departure would be bigger. But I'm just speculating.
Yeah, so maybe you went kind of like fast on the extension, but here in this framework, climate only affect the economy through productivity losses. But what about, I mean, based on your previous work, if also that affects directly, let's say, amenities for a representative household or other margins that could affect the economy?
Yes, that's a good point. I mean, one effect on amenities that's or on effective amenities that's very much in the literature is mortality. I mean, you can, you know, that's just a loss of, you know, flow of utility. So there, I think it really depends on the shape of the utility function, because that governs the marginal rate of substitution between consumption and, you know, the ability to live a longer life. And so I suspect that under log utility, you can still construct a BGP with mortality or amenity losses. I think away from log, it gets harder. And so obviously, you know, Pete and Chad have worked a lot on that. So at some point I'll have to ask them how to do it. And then you can also think about capital depreciation. To some extent, you know, damages on capital depreciation will be isomorphic to productivity for long-run changes. You know, if you think about the RBC model formula where, you know, output is equal to productivity to some elasticity divided by a rho plus the depreciation rate, you can kind of see that the loss in productivity over long horizons is isomorphic to an increase in the capital depreciation rate. We had a paper by Tillman making that point yesterday. Pete.
Does it work? Now it works. Sam, we need the trade person to fix it. Okay, so GHKT, Golosov, Hassler, Krusell, Savinsky, they get the optimal carbon tax that gets net zero. And they do it, and Ishan touched on this, by saying, and maybe this is just extrapolating too much for you guys, but they basically say every increment to the carbon stock has a fixed percentage reduction in output. So then basically the output percentage damage is accelerating if you have the situation you have here where temperature is rising linearly. So the optimal thing. So why don't you incorporate that more as one of your scenarios?
Yes, so you're exactly right that the particular damage function that Golosov et al. Use is very convex in practice because they sort of don't think about the Arrhenius law, this log scaling of temperature with the carbon stock. And so if you recast their damage function with kind of the proper quote unquote climate system, they have a super exponential damage function. So their damage function is like exponential of temperature. Now you may think that the damage function is indeed that convex. And so we've actually worked that out. So we then solve our model. So let me show you two things. The first one is how the theory changes when you have a nonlinear damage function like that. So we can classify damage functions into our baseline, which is log linear, log concave, where marginal damages fall as temperatures rise, and then log convex damage functions. And so the Golosov damage function would be in here, where marginal damages rise as temperature increase. And so in the log convex case, you recover exactly the numerical results that they find, which is that our results become even more extreme. And so under the log convex case, growth basically stops because of climate change in the long run. And then the planner wants to move even more aggressively to allow to recover a positive economic growth. Now you can say, well, that's only in the long run limit. And so what happens numerically? And so I think one thing that's useful to see is okay, so then you can take our quantified model and then recalibrate it to the same empirical targets, but using the functional form of the Golosov damage function. So this is what we do here. So this figure shows you marginal damages as a function of a change in temperature, recalibrated to three cases. The flat horizontal line is our baseline, so log linear damages. The dashed blue line is if you take the Nordhaus damage function, so it's log concave. And then the blue line is the Golosov et al. Damage function. And so you can see that as soon as you move towards like even 4 or 5 degrees of warming, the marginal damages with this functional form like rise very steeply. And so then you can ask, okay, what happens for over the long run if I put in that damage function in the model? And so now we're going to year 3000. Okay, so bear with me. This is just to illustrate what's happening. And so the solid blue line is our baseline, where you have a drag on economic growth from climate change. The dashed line is what happens under the Nordhaus damage function, which is log concave. And so initially it looks sort of the same. And then in the long run, growth is independent from climate change in the log concave case. And then this is the Golosov damage function. And so you see that for the first 200 years, it's similar, but then growth stops. And that's because the nonlinearity eats up all possible growth. Yes.
So I was just curious about, adaptation. I mean, I know in policy institutions like the Fund and the World Bank, for low-income countries in particular, that's what they're really focused on, is getting money. And now, I don't know if we know enough about the effectiveness of adaptation in the very long run once you're looking at the kind of scenarios you're looking at, but is there a sense in which that's another margin that could shape these things, or how do you think about that?
No, that's a great question. I think, to echo what Ishan was saying, we need to know more about the really crazy stuff that might happen at very high levels of warming. Similarly, we need to learn, to figure out what's the impact of adaptation and how much it costs. You can interpret, so in here, a log concave damage function, one that rises less than 1-for-1 with temperature, you can interpret it as unmodeled adaptation. Then, of course, the exact shape and where it concavifies matters a lot. But here, at least for the Nordhaus damage function, which is log concave, you can see that at least for the foreseeable future to 2200, it's sort of similar. Maybe we'll have explosive growth because of AI before then, but we'll see.
This might be one of your extensions, but have you thought much about this Cobb-Douglas assumption for energy versus capital and labor? So, usually we think about energy in the short run as being complementary, and maybe in the long run as being substitutable with directed technical change. Does that change things? And two, especially with the price of energy going up in the long term. I mean, Ishan's graph was cool, but it's a little misleading in that fossil fuel prices are way up since the 1970s, even though we've found much, much more. So do you think about building in changes in the actual price of energy?
Yes, so two great questions. So let me take them in reverse order. So for changes in the price of energy, that's our chi-t. And so we're matching the trend in the price of energy, and that gives us the trend in chi-t, and then we kind of stick that into the long run counterfactual. So that's exactly how we're getting the extraction cost. And then your first question on substitutability, I mean, that's a really important point. You can, when we were looking at the intuition here, you can sort of see that it's important that I can connect the average product of energy to its marginal product. And so this is where Cobb-Douglas helps. So for us, what really only matters is that the energy share kind of converges to a finite value. If it in the long run goes to zero, then that kind of removes the second regime. And so what matters is this long run value. So if you think it's zero as the world gets richer, then you can forget about the second regime. If you think it's positive, maybe below what we have now, then you should use this sort of lower value. And then I'll also just say that the Hassler et al. Paper shows that it seems pretty Cobb-Douglas. I mean, yes, in the short run, it's more complementary than that, but the energy share has been relatively stable over time, at least in the data they report, and they interpret that as directed technical change, bringing us back to close to Cobb-Douglas. Yes, Tommaso.
So a couple of questions, I guess a question and a comment. So first, my question is, if I understand correctly, there is a horse race between growth into energy demands and carbon savings technology. And so how much uncertainty there is in this exogenous growth rate in carbon savings technology, and then can be another thing that a planner could do rather than just put a cap on the growth of the economy, just try to incentivize carbon savings technology, carbon capture, and so on and so forth.
Yes.
And then I guess the second question is, I would love you to address the alligator point, as in, address this. How do you guys think about this, massive heterogeneity, projecting with this model into a world where you're gonna have alligators at the North Pole, that's how are you thinking about this exercise?
No, great point. So yes, so of course the planner can do. You can. Let me get this slide. So we have an extension where there is endogenous innovation in renewables, and so as long as the planner has two instruments at their disposal, like kind of the carbon tax and an innovation subsidy, qualitatively the regimes look pretty similar. So even if you can subsidize innovation in renewables, you still want to impose a carbon price. And we show that even in this case, you still have kind of the regime switch for the carbon price. Now, of course, the exact formulas are going to change a little bit because endogenous innovation in renewables matters, but you're still going to have the regime switch in carbon pricing. Now, that being said, what I think would be very interesting, which would answer your question, would be for constrained planners to solve the Ramsey problem, in which you cannot have the the efficient innovation subsidy. If you only have a carbon price, what happens? And then the reverse, if you don't have a carbon price and you can only move around the the R&D subsidy in the renewable sector, what happens? So those we haven't worked out, and I think that would answer exactly your question. To the alligators, yes, I mean, I totally agree. This is really important. By definition, tipping points. So, the stuff that happens only once you reach a certain threshold, it's very hard to learn about that historically. So you can either rely more on models, or you can go back to these historical papers that go back 55 million years to maybe draw some inspiration, but it's inherently very difficult. And so I think it's important. You can explore different functional forms for the damage function, which is what we're just looking at with Pete. But other than that, it will always be somewhat speculative. Noémie.
So maybe related to that, like I feel Ishan really emphasized that both in terms of the damage function and also the behavior of the climate system, there's just a ton of uncertainty, especially in the long run. And is there any way you can characterize a planner's problem under uncertainty? Like what if at this stage the planner just doesn't know and have to make the optimal decision given that?
I think it's a very important point. I think if it's a one-off uncertainty, like I commit now and then the whole dynamic path unwinds, I think that's feasible. But then if the uncertainty resolves gradually over time, I think that's difficult. I mean, I have some work with Santi, who's in the room, on precisely that type of uncertainty. But these things are difficult. That said, I will emphasize that yes, people disagree about the climate sensitivity, but the order of magnitude of that uncertainty is around 3 degrees. It's maybe kind of 1.5 to 4.5. So it's there, it's meaningful, but it's not massive relative to, say, the IES, where maybe the people disagree, from 0.1 to 20. And so there's also lots of uncertainty in other important objects, including the damage function, that I think is just as important, or policy uncertainty, which I think in this case dwarfs much of the other sources of uncertainty. Chad.
Yeah, no, I found it very interesting. I'm shocked that in your world where damages are so large and they accumulate forever, that we say, yeah, after 2300 we burn the world and forget about the future, and it seems to me we probably won't do that. The natural thing, you have it on your bullet and you talked about it a little bit, it's just this endogenous innovation. So in a paper with Pete and Maya Eden that we're working on an optimal population, we've got a little climate block, and we took the GHKT damage function. So we're making the damages, accumulate even faster. And in our setup, the social planner wants to invent new ideas very, very quickly to solve that problem, because it's a permanent problem. As Ishan and as your paper emphasizes, every bit of damage you put out there hurts everyone forever. And so in our setup, endogenizing the technology means just solve that as quickly as possible, and then you can forget about it. So I'm sort of wondering a little bit about why that's not what happens in your setup. And it could be the GHKT thing, but I don't know.
Yes, so it's a combination of two things. One is the Golosov et al. Damage function, which you've seen just become so nonlinear that the damages become massive under any baseline calibration. That's one. And then the other one is, of course, the elasticity of substitution between renewables and the rest and other sources of energy. And so that, I think, is, the jury's still out to figure out whether it's one or, I think it's above one, but then how much above one it is. And so that's important. And so we don't really take a strong stance on this elasticity of substitution. There's the famous paper by Philippe and Deron that precisely makes that point. So we think that's more sort of, a separate point from the one we're making. And the last thing I'll say is, so yes, the planner does tolerate, continuous warming here, even when damages are large, but, 0.4 degrees per century, even if you fast forward to 2600, that's still not a ton of warming relative to what a planner, what happens under the laissez-faire, which is, basically all of the warming that you would get under the planner here to 2600, you would get in basically 1 century in the laissez-faire.
Oh, but when you can have solar panels and small nuclear reactors and fusion and batteries, it feels like this is a problem that's definitely solvable. I agree the equilibrium doesn't seem like maybe it's going to solve it as soon as it should, but it feels like in 100 years, are we not going to solve that problem? I really hope so.
Yeah, I'm with you. So again, I think this is almost like a separate point from the main point we're making this paper, but I'm totally with you. So that's why, what we also do is we look at what happens if a backstop technology, say nuclear fusion, solves everything, and we introduce this backstop technology at different dates, precisely because we think, that's a plausible scenario as well. And so what you see is interesting is that, our results kind of apply approximately until the backstop arrives. And so you can take our formulas as good approximations for what happens. If the backstop occurs in 2050, then our formulas apply prior to 2050. If the backstop arrives in 2100, then our formulas apply until 2100. And then, of course, once you have the backstop, that kind of kills the climate change problem. And so then the economy starts growing at a different rate.
Yeah, that's helpful. Thanks.
On that, be a 15-minute break and back and Yes. All right, guys. Yes. Welcome back. Two papers left. I know this has been a long day. Okay, so we got two papers left on the environment and growth, and we're going to start with you and me, about growth firm scale and the energy intensity production.
Cool. Well, thanks a ton to the organizers for having our paper on the program. So this is joint work with Connor Walsh and Katie McDonald, the fantastic PhD student at Columbia, and they're both in the room. So the starting point of this paper is the idea that as long as production requires energy and energy use emits CO2, there exists a fundamental trade-off between economic growth and environmental sustainability. A key determinant of this trade-off is the energy intensity of production, E over Y, the amount of energy required to produce a unit of output. Now, this quantity is far from being constant over time, and the good news is it's fallen quite a bit since the 1990s, by roughly 35% at the global level. This is the blue line on this chart. And let me say from the start that this decline is not driven by reallocation of economic activity across sectors. It's mostly a within sector phenomenon. What you can also see on this graph is that the decline in energy intensity is the key driver of the contemporaneous decline in CO2 over Y, the CO2 intensity of production, the climate relevant variable. And this is because CO2 over energy, so how dirty your fuel mix is, the green line has remained mostly flat over time with just a small decline after 2010. So the key reason why we emit less CO2 per unit of GDP is really because we use less energy per unit of GDP. That's for the time series. In addition, when you look at the cross-section of countries, energy intensity fell the most in countries that grew the fastest. What we do in this paper is uncover a mechanism through which economic growth endogenously leads to a decline in energy intensity, rationalizing the two figures I've just shown you. This mechanism rests on two facts. First, the known fact that average firm size increases as countries grow. And second, the key novel fact in this paper is that we show that the energy expenditure share and thereby energy intensity both decline steeply with firm size. Together, these facts imply that energy intensity endogenously falls as countries grow. To establish this, we proceed in two steps. First, we use firm-level data from India to document a negative causal effect of firm size on the energy expenditure share and energy intensity. We show that this result is best rationalized by a non-homotheticity in the production function and can be explained by two distinct mechanisms within technology physical scaling laws and discrete technological improvements as firms grow. To assess the aggregate implications of the scale dependence in energy use, we develop a heterogeneous model where the one non-standard ingredient is that the production function is non-homothetic, calibrated to match our empirical evidence. And we find that this channel is very powerful at the aggregate level. For India, the scaling up channels implies a 50% drop in energy intensity over the last 30 years. And projecting forward, these channels reduces India's energy demand at the 2050 horizon by roughly half. So let me just jump right in, empirical evidence on firm size and energy demand. The data we use in this paper is the Indian Annual Survey of Industries. This is a representative survey of the formal manufacturing sector. And for our purpose, the key advantage of the ASI is that firms report their expenditures on energy inputs with a price quantity breakdown, which allows us to reconstruct Indian aggregate manufacturing energy use from the bottom up. Why India? Well, we think that this question of the trade-off between growth and the environment is all the more important in the context of low and middle income countries where growth is really the key engine to raise living standards. And at the same time, these countries are already significant contributors to global emissions. And so in that respect, so India, one, is kind of representative of LMICs when it comes to energy intensity. And second, is important in and of itself due to its size and projected growth trajectory. So let's now look at the Indian data. What you have here is energy intensity on the left-hand side, so the climate relevant variable. And on the right-hand side, the energy expenditure share, our key mechanism in the ASI data since the 1990s. The way we define the energy expenditure share is expenditures on energy inputs divided by expenditures on energy and other inputs where the denominator can be either total costs, that's in blue, just the cost of energy, materials, and labor in red, or energy and materials in green. And what you can see is that irrespective of the denominator you choose, the energy expenditure has fallen by roughly 50% over our sample period. Let's now look at the same energy expenditure, but in the cross-section of firms, which is our main point here. So what we do here is we plot the average energy share by deciles of firm size when these deciles are taken within industry year sales. And what's really striking from this graph is that the energy expenditure essentially monotonically declines in firm size, irrespective of the definition. Taking the red dots, which we're going to use as a baseline to avoid measurement issues with the cost of capital, firms in the 10th decile have an energy share that's roughly half of that of firms in the first decile. Now, unfortunately, this cannot be readily interpreted as a causal effect of firm size on the energy share. The main identification constraint here being that that firm size may correlate with other variables that directly affect energy shares. So, think small versus large firms face different energy prices or have different factor-specific productivities. Both would affect the energy share under non-unitary substitution across inputs. So to get at this causal effect, we proceed as follows. We're going to estimate regressions where we regress the change in the log energy share relative to the share of other inputs on the log change in firm size as proxied by sales. And the important thing is that we're going to instrument the change in firm size with firm-level demand shocks. This instrument is a shift-share style instrument that interacts national-level changes in product-level sales with firm-specific ex-ante product shares. The intuition being that a firm will tend to grow more if it's ex-ante specialized in products that grow faster over these 8 years. The identifying assumption here is that this instrument is orthogonal to the unobserved determinants of the energy share, and we provide a large number of tests that support these assumptions that we'll happy to discuss more in the Q&A. So these are our main results. You have on the first 3 columns OLS results. The last 3 columns are IVs. We're showing results for the 3 different denominators I showed you before. And here we show results at a 5-year horizon, but results are very similar at a 3, 5, and 7-year horizon. The way to read his number, taking our baseline specification, is that a 10% increase in output reduces the energy expenditure share by roughly 4%. A number of additional results that I'll just walk you through because I don't have the time to show them all in details, but that are important to interpret our main findings. First, this effect of firm size on the expenditure share is not mediated by changes in relative factor prices as firms grow, i.e. it is really a direct scale elasticity, so non-homotheticity, as opposed to an indirect effect via substitution. Second, the decline in the energy share directly translates into a decline in energy intensity as firms grow. So the elasticity of E over Y with respect to growth in Y, so quantity growth, is roughly minus 0.4, very similar to the expenditure share elasticity. Third, our results are robust to considering only firms that produce the exact same products and use the exact same inputs at TNT plus 5. So they're not driven by composition effects or firms just changing the set of production steps that they do as they grow. And finally, when investigating how the energy share falls with size, we find that it falls primarily relative to materials. So what does that mean? Consider a brick producer that combines clay and fuel to produce bricks. As this firm scales up, it requires less fuel to process a given quantity of clay. Now, this decline in the energy to material ratio may suggest an increase in firms' indirect use of energy that is embedded through their material inputs, and that could partially offset the decline in the direct use of energy. So to get at that, we construct a firm's total energy use, summing the direct and indirect component, and we show that it also declines with firm size. All right, so I've shown you our main results. What's going on here? Well, essentially 2 things could be going on. One is that within a given technology, there's increasing returns to energy use. Why would that be the case? Well, the key force here is physical scaling laws that imply reduced losses at higher scales. Let me just give you an example. Take a cupola furnace of a given design and increase its size by 50%, you're going to reduce energy used per ton of molten metal by roughly 10%. Why? Because here, a lot of energy used is lost to heat dissipation, and those heat loss scale with the surface of the furnace, while what you produce, the molten metal, scales with the volume of the furnace. And so just by the virtue of physics, producing at higher scale is more energy efficient. How much of our measured elasticity can that explain? To get at that, we use engineering models of representative technologies within each energy end-use class. And for each of these technologies, we derive these purely physical scale elasticities and take their weighted average across energy end-use classes to obtain that these physical scaling laws can explain roughly a minus 0.1 elasticity. So absolutely not all of our effect, but more like 25% of what we see in the data. So what else could be going on? Well, the other thing that could happen is that as firms grow, they upgrade their technology towards more energy efficient options. Think of firms as facing a menu of technologies they can choose from when they produce. What we show is that a feature of these technological menus is that more energy efficient technologies tend to require larger fixed costs. To document this, we collect data on these technology menus for a number of manufacturing industries for India. And here is how to read this graph. On the x-axis, you have the fixed cost of investing in various technological options for a typical foundry in India, where, for instance, one dot is a lead mechanism that you can put on your furnace to reduce heat dissipation, or all the way up here, you can replace your cupola furnace with a much more energy efficient electric induction furnace. On the y-axis, you have annual energy savings when investing in these technological options, keeping production constant. And so this positive slope here means that more energy efficient technologies tend to require larger fixed costs. What that means is that larger firms will optimally choose to adopt more energy efficient technologies. And this is something we can see directly in the data using an independent World Bank survey on energy efficiency investments by Indian firms. How much of our effect can that explain? Well, using this technology menu data to parameterize the trade-off between the fixed cost and the marginal energy saving, and assuming firms make the optimal technology decision, we can show that this can generate a scale elasticity around minus 0.3, so roughly 75% of what we see in the data. So together, these two mechanisms quantitatively rationalize our findings. And I want to stress that there's really nothing mechanical here because this comes from fully independent strategies from our main estimates. How does this scale dependence in energy use affect energy intensity along the growth path? So here, I'll first show you a simplified version of the model that is just very useful to convey key intuitions, and then to produce quantitative results, we'll go to the general version. So in the simplified version, the production function is Leontief in materials M and energy E, and the production function embeds the two mechanisms we've just discussed. One, if this parameter epsilon is negative, the production function will display within technology physical scaling laws, i.e. for a given technology, as the firm scale up, energy intensity is going to go down. Second, firms choose a technology that is indexed by phi, where a higher phi means that you produce more output per unit of energy. This technology has a cost that varies with phi with elasticity gamma with the scale at which you want to produce with elasticity delta and is paid for in capital and labor. So the interpretation of delta is that if delta equals 1, this technological choice behaves like a fully variable cost. But if delta is small, the technological choice behaves like a fixed cost problem. With this, we can characterize the optimized cost function of the firm. And the key thing what I want you to see is that the cost of energy, capital, and labor scales with output with elasticity 1 plus epsilon tilde, where epsilon tilde takes this form. That means that this share of the cost is going to scale less fast than output if epsilon tilde is negative. And that can happen for two reasons. Either, even if the technological choice is a variable cost problem, having the physical returns is enough for this elasticity to be negative. Or alternatively, forget about the physical scaling laws. having the technological choice problem behaving like a fixed cost problem is also sufficient to generate this scale elasticity at the firm level. Then the energy and the non-material cost share both depend on scale. So here, because of the simplifying Cobb-Douglas assumption, the energy share is just proportional to the non-material share. The general model will relax that. And the non-material share takes this expression with a first term depending on relative factor prices capturing substitution effects, and a second term capturing the scale effect. So you see that this looks very similar to the estimating equation from our empirical analysis, where what we estimate is precisely the scale elasticity. And so our empirical exercise, in fact, estimates that the scale elasticity is negative. To take this model to the data, we're going to essentially use just a much more general version of this cost function. Namely, we allow for generic elasticity of substitutions between material and other inputs and energy and the capital labor bundle. We allow each input to have its own scale elasticity, knowing that in conjunction, they control returns to scale at the firm level. And we allow for exogenous factor-specific productivity shifters that allow us to match factor shares in an initial year. The rest of the model is that the final good is a CES aggregator of firm varieties, where the number of varieties is pinned down by fixed costs paid in unit of labor. Capital, materials, and energy are produced from the final good at exogenous rates. So as in the data, firms use energy both directly and indirectly through their inputs. And finally, labor supply is exogenous. So with this apparatus, we can ask, how does economic growth affect energy intensity? And more precisely, the exercise we do is that we feed in data on labor supply, calibrate AY, so factor neutral TFP growth, to perfectly match output growth in the data, and ask what happens to all endogenous variables. I'll be quick on the calibration, but just 2 points. The scale elasticities are estimated using moments very similar to the ones I've shown you in the empirical section. We also need to estimate substitution elasticities. And the key takeaway here is that energy is a strong complement to other inputs. So this is what we get. One, by construction, we exactly match output in the data. So model is a solid blue line, data is a dashed red. More interesting, on the right-hand side, you see that average firm size increases in the model. So in the model, this is because fixed costs are paid in unit of labor. And you see that this parsimonious assumption allows us to match the data time series pretty well, which is important here because average firm size is really the forcing variable behind our mechanism. This is our key result. We find that the model predicts a 45% decline in the energy expenditure share over our sample period. This is large, and this is entirely driven by the non-homotheticity. In the gray line, we show a homothetic CS benchmark, and there you see that the energy share barely moves. To compare model and data, we want to take into account the fact that in the data, the relative price of energy has increased over time. So to do so, we change the exogenous parameters determining relative factor prices to match what we see in the data. And that's now in the green line. So what you can see here is that in this version where model and data are most comparable, the energy share moves by less. This is because the relative price of energy went up and energy is a complement with everything else. And we explain roughly 65% of the decline observed in the data. What that also means is that had the relative price of energy not gone up in India over our sample, the decline in the expenditure share would have been even bigger, right, by roughly 35%. The decline in the energy expenditure share readily translates into a decline in energy intensity defined either as energy over output or energy over value added, with a magnitude that's roughly a decline by 50% in the version of the model, keeping factor prices fixed. Finally, a key implication of having an endogenous relationship between growth and energy intensity is that we can expect the trends we've seen to continue in the future. And so we use our model to do projection exercises. Namely, we feed projections on labor force growth and output growth and ask the model to predict energy use at the 2050 horizon. And what this shows is that our baseline model projection, which is in blue, predicts energy use at the 2050 horizon that is roughly 50% lower than in a benchmark model assuming constant energy shares, which is mostly what international agencies trying to predict CO2 emissions use. To conclude, the key contribution of this paper is to propose a novel mechanism linking economic growth to a fall in energy intensity that relies on two facts: an increase in average firm size as countries grow, and the expenditure and energy intensity falling steeply with firm size. This mechanism is powerful quantitatively at the aggregate level. And to end on a note maybe a little bit more optimistic than the previous paper, we think that what this paper says at the end of the day is that the trade-off between growth and environmental outcomes endogenously improves as low and middle income countries grow. And a very concrete implication is that the build-out of renewable energy that's needed is maybe less challenging than previously thought. Thank you very much, and I'm looking forward to Johannes' discussion.
Great, thanks. So the discussant is Johannes.
Okay, great. Thank you so much for asking me to discuss this really interesting paper. So Noemi has been very clear in her presentation. So the paper is using data on Indian manufacturing firms, strictly speaking, manufacturing plants, to show, first of all, there's kind of a contribution on the micro level, and then afterwards we do from micro to macro. So at the micro level, they're finding a non-homogeneity in energy use at the plant level. So in the OLS, that's a negative correlation between the energy share in different types of costs, and firm scale. Okay, and then they're showing IB regressions to make the argument that there's a causal channel from firm scale to the energy share or energy intensity of production, in the sense that if you get a positive demand shock, the energy share of production is shrinking. Okay, and quantitatively, that's actually quite meaningful. So a 1% increase in output reduces the energy per unit of output by about 0.4%. Okay, and then they're talking, and I think that's a very nice part of the paper. They're talking about two sources of kind of mechanisms that could give rise to these non-homogeneities. One is physical scaling laws. So the way I think about it is I'm standing at the barbecue and I'm making sausages. Okay, and I have to use coal for the barbecue. And if I want to make twice as many sausages, I don't actually need twice as much coal. I need less than that. Okay, partly it's because of the heating up. Partly maybe I can use the barbecue more efficiently. But you know, it kind of makes sense to me. I mean, if I want to make twice as many sausages, I don't use twice as much coal. Okay, and the second mechanism are these fixed cost investments. Okay, so you can upgrade your furnace, your barbecue if you want, and maybe there's a fixed cost to pay for these things, and then afterwards that's going to decrease the energy required and the fuel required for production. So that's the micro part. And then they're doing a micro to macro quantification of that non-homogeneity in the course of the Indian growth process between 1990 and 2023. So they're showing a simple GE model. So the shining part of the model really is the production function, because they're adding a lot of bells and whistles and so on, substitutability, whatnot. But they're really using that to show that this non-homogeneity is something that matters also and that shows up on the aggregate level. So this is not just a curious micro fact for the microeconomists, but it's also something that people in this room might actually care about. Okay, and they're finding that disciplined by these early estimates, the IB estimates that non-homogeneity accounts for a large share of the decline in the Indian manufacturing sector's energy share of production. Okay, so why is this important? Two exhibits. One, and I have to make this point, I'm sorry, is still not completely clear among people in the world, maybe not so much in this room, but in the world, that actually growth is something that is important. Okay, so there was a recent letter by some economists, including some serious economists, that growth is a doomed strategy. There is a better way. So I think one thing that this paper is doing very nicely is arguing that growth at the firm level is very important for the energy share of production. And there are many reasons why we would care about the energy share of production. And Adrien and Ishan have spoken very I mean, cost reductions are also good reasons. Productivity, right?
That's different. Keep going.
Okay, I apologize.
Think about what they say, it's worse.
I knew that this slide would cause controversy. Okay. So secondly, I mean, I know that they want to extrapolate this to beyond India, and I think that's an important thing. But at the very least, I mean, the country that they're studying is going to become, or at least is projected to become, one of the world's most important consumers of energy. So, you know, this is from the International Energy Outlook. They're projecting that by around 2050, India is expected to overtake the US when it comes to consumption of primary energy. Okay? So this setting is actually very important. Okay? So I think this is an excellent and very thought-provoking paper. It makes, in my view, a very convincing case that the organization of production at the microeconomic level actually matters for the aggregate energy use and for emissions, even at the aggregate level. Okay? So I happen to have used the same data that Neumann and Crothers are using in the past. So effectively, what I'm going to do is I'm going to replicate the results. Okay? And I'm going to discuss a little bit robustness and interpretation. So robustness at the microeconomic level, and I'm going to show you some more results at the macroeconomic level as well. Okay. So first, I'll show you some more facts about this cross-sectional relationship between energy share and size. I'll talk a little bit about the RV, and then at the macro level, I want to do a decomposition of the empirical aggregate energy share into within-firm changes and across-firm changes. They're doing in the paper also a decomposition, but the decomposition of the outcomes of the model, and I want to contrast that to the decomposition that I find in the data. Okay, so first of all, before I do the replication at the micro level, I want to say, so I'm trying to do this as closely as possible to what the authors are using in terms of the sample, but it's not going to be exactly the same thing. So I'm going to use data from 2001 to 2015 only, partly because the earlier years of the ASI have several measurement problems when it comes to intermediate input. So I think those years are actually much cleaner. And also the earlier years sometimes include power plants establishments. And for obvious reasons, I mean, that might be kind of confounding things a little bit here, okay? I'm also not going to use sampling weight. So, you know, there's some caveats when it comes to the representativeness of that sample. Maybe there are also some smaller differences as well. So first of all, this is the cross-sectional and also within-firm relationship that I get between scale of production, so as measured by sales, and various forms of energy shares in different aggregates of costs, so labor plus materials, and you add capital as well. And then you can also look at compared to value added, and then also aggregates, but where the material shares are not in there. Okay? And this is actually a table that they're running exactly the same specification, so don't be scared by kind of not finding the same sign here. But generally, whenever you compare the energy expenditure to something that includes materials, you find a negative coefficient. You also find a negative coefficient if you look at compared to value added, but you don't find that if you don't include the materials expenditures in the cost basket in the denominator. So in that sense, the way I would interpret that is that in the cross-section, energy expenditure relative to materials is lower for larger firms, or in the within-firm relationship as firms are growing, the energy share compared to materials is falling. Okay? So the first thing that I thought about, and maybe this is my personal bias, is that is this perhaps confounded by other changes in organization of production? So Ezra and I have a paper where we are arguing that as plants are growing, they're starting to become more vertically specialized in the sense that they're dropping several steps in the production process. So for instance, a plant might be producing polyester yarn from plastic waste, and then first they're melting the plastic waste into granules, and then afterwards they're converting that into polyester yarn, and they're using heat at each step in the production process. So then if they're getting a positive demand shock, then they would only do the last bit in the production process, so from granules to polyester yarn. Maybe that's why the energy share of production is lower or is falling in the within-firm relationship. Right? So effectively, what I try to do is I try to do the cleanest thing in terms of how I can think of holding the production function constant as what these plants are actually doing. Okay? So I'm running the same regression. So here's the OLS, but the same thing holds in the IV. Okay, and I'm gonna condition on, first of all, single product plants, so firms that only produce one 3-digit product category, and I'm gonna also condition on exactly the same mix of 5-digit intermediate inputs. So I'm really holding inputs and outputs completely constant, and there's only one output. Okay, and you still find, and in fact, the negative coefficient gets even larger if you look at within that. So what I would take away from that is that at least, this non-homogeneity is not coming from changes in the set of vertically related tasks that these firms are performing as measured by the extensive margin of the product mix. Okay? But I still find it kind of interesting, and at least to me surprising, that energy compared to labor inputs does not fall with scale. Okay, because you have here this maybe positive or maybe close to zero coefficient. Okay, so in that sense, I mean, if there's kind of like some fixed cost of heating up, the furnace, that's independent of how many sausages you're producing, if you want. If there are these overheads, maybe there's some overheads in there for labor as well. But at least when I think about the different channels, if I think about me being on the barbecue, if I do twice as many sausages, probably I'm also going to be somewhat close to twice as long at the time, standing at the barbecue making the sausages. Yeah? So in that sense, maybe it's a feature of the Indian labor market. Maybe labor is so inelastic that it's very difficult to fire permanent workers, or it's very, firms are very, very unwilling to hire more permanent workers, which they would require in order to scale up the labor input as well. And that's why labor is not responding to so much. But it's something that I thought would be interesting to find out and see also whether that's the case in other settings as well. The other thing, and that's maybe just a side point, is that there are other things that are also correlated with the energy intensity. So establishment age. So effectively in these regressions, I'm controlling for a polynomial in large sales, and you still find that establishment age is very, very significantly correlated with the energy share of production. Okay, so maybe there's also some sort of life cycle, vintage capital thing involved in the determination of the energy share. Okay. Okay, so then for the IV, so the interpretation as a non-homogeneity rests on causality. So they're using this shift share instrument. So it's a weighted average of product level sales in India in a given year. So the changes in that, and the weights are the firm's sales shares on those different products. Okay, so that's a firm level variation because those product shares are idiosyncratic to the firm, and that generates idiosyncratic variation. The drawback of using that instrument is in general, these large sales will include also product or industry specific supply shocks, cost shocks to the inputs, for instance, and therefore it's not purely necessarily a change in the demand. Okay, so that's one potential caveat with that instrument. The second thing is that mechanically there's going to be the sales of the firm itself also in the instrument. So maybe you want to be a little bit cleaner and actually exclude those. So if you do that, so that's what I try to do. I try to hit these results with anything I could find. And in fact, the first stage F, I got something initially of something above 100. And if you exclude the sales of the firm itself, the F drops a lot. It's not dropping to below 10, so it's still fine by sort of conventional standards. And interestingly and importantly, the coefficient is not very much affected. Okay, so just I would say, be cleaner, leave out the sales of the firm itself. It doesn't seem to have any particular impact. Okay? So I mentioned I really like this kind of more micro explanations for why we would see why we would expect to find this scale economy. So the physical scaling laws and the technology manuals. So for the physical scaling laws, I wanted to mention another paper just because I like the paper a lot. I think it's a very nice one. It's called Iceberg Transport Costs, and it's a study of the ice shipping industry, which was headquartered around Boston here in the 19th century. Okay, so there was this gentleman Frederick Tudor who had the very badass nickname, the Ice King. Okay. And he set up the Tudor Ice Company, and he harvested ice from lakes in New England. Okay, so you can see people kind of cutting out these blocks of ice, and people laughed at him, right, initially. But he effectively started shipping those blocks of ice across the world, all the way to South America and even to India. And initially, he was not very successful, and people, laughed at him. But at some point, this enterprise actually became profitable. Okay. So the ice was mostly used for refrigeration. So in Kolkata, there's still kind of this storage house where they used to store the ice. And of course, as part of that shipping process, some of the ice melted away. And that's exactly the relationship to this paper. There's a physical scaling law here as well. So there's this beautiful paper in the Economic Journal by by two authors, where they are getting access to the company records from this company, which are in the beta library at HBS, and they're getting data on the costs of the shipping and the packing and the unloading, and voila, what they find is exactly a physical scaling law, right? Because the right way, the ideal way to minimize the amount of surface of ice would be to have a ball of ice, right? That's minimizing the surface area and therefore the heat loss. Unfortunately, of course, ships are not ball formed, okay? So they couldn't do that in the ideal way. But still, they took records of how much ice melted on the shipments to Kolkata, and overall how much they had to pay workers to insulate the ice. So they were using sawdust to insulate them. And you really find indeed kind of that trade costs are not iceberg, literally. And there's these physical scaling laws. Okay. Now, from the micro to the macro, so in the full quantitative model, Noemi and co-authors are using this production function that includes energy, materials, and a bundle of capital and labor. And there are these different elasticities that give you the non-homogeneity associated for each of those different factor inputs. Okay? And they're estimating that for the IV. And they're estimating also these elasticities of substitution with changes in the price indices. And then they effectively do an exercise where they feed in the aggregate productivity to match the overall increase in output of the Indian manufacturing sector. And then they see what they can match. Okay? So they actually find that this non-homogeneity mechanism is quantitatively very important. I like this exercise a lot because I think it's the most direct quantification of their channel. They're doing a second exercise where they are also trying to fit the prices of the different factor inputs. And they're kind of modeling the factor supply in a very, very, let's say, simple way, maybe a little bit too simple. So there I find this exercise much harder to interpret, just because we don't really know where these price indices changes are coming from. Are they really coming from changes in the productivity in the supply of these factors or not? And I think that's a little bit more involved. But effectively, to think more about the relevance of this channel, I want to show you an empirical decomposition of the factor share. So I'm going to take the aggregate factor share in India at the beginning of my sample, so that's the beginning of the 2000s, and then in the 2010s, so about 10 years later. Okay? I'm going to decompose changes in this aggregate energy share, this is in total cost, by the way, into a within plant or within firm change, into a reallocation term. So for a given energy share, is that correlated with the growth of the plants? And then there's also entry and exit. Could be that the firms or the plants that are coming in have different energy intensity, or the ones that are leaving have different energy intensities, and how that is shaping. Okay. So here's the result of this decomposition. Okay. So you see that the within term is accounting for about, I think, 47% of the total change in the cost share. You see also that this relocation term is accounting for also 50-something, or like 65% actually. And entry and exit does not matter very much. Okay, and together both of those things are accounting for even a little bit more of the total decline in the energy share. Okay, and then what I try to do is to take the elasticity that they're using in the paper for the non-homogeneity and multiply this by the average increase in firm scale that we're having over that time period, and you find a number that's very, very close to this within decomposition term. Okay, so in that sense, the non-homogeneity that they are estimating seems to be quite consistent with that decomposition as well. And that convinces me that, this is indeed something that's a big part of that overall decline in the energy cost share. But at the same time, there's also this relocation term. And that relocation term is absolutely not present in the model. Okay, it's effectively kicked out. And I tried to decompose it a little bit further. Is that within an industry, plants that have a lower energy share are disproportionately growing faster? And the answer is no, that's not the case. It's in particular, it seems to be an across industry term. So there's a little bit of a structural transformation story in the sense that industries that have a lower energy intensity on average are growing a little bit faster over that time horizon. Okay, so that the model doesn't feature any industry, but if you wanted to account for everything, then maybe thinking about the industry mix could be important as well. So in that sense, I wouldn't necessarily take the statement of the paper at face value that the non-homogeneity accounts for almost all of the decline, but it does account for a big part of the decline, and I would agree with the statement that that non-homogeneity is important at the aggregate level. Okay. The paper is doing some exercises where they're looking at whether the energy that is embodied in the material inputs, which we've seen is also important in explaining these changes in the shares, could be important. So they've looked at that at the micro level. I would love to know, is this something that we should also think about when we want to think about the aggregates? And then finally, the paper is performing some of those exercises where there's, for instance, making statements like, without the non-homogeneity, India's energy demand by 2050 would be twice as high, or accounting for the non-homogeneity, India's CO2 over energy ratio could actually expand, and it would still be able to meet the Paris Agreement goals. Now, I think it's great to be enthusiastic about the findings of the paper. I think they're fantastic, but I want to caution these statements a little bit, because effectively those statements require that the manufacturing sector is representative for the whole for the entire Indian economy, which is probably not the case. So manufacturing plus construction plus electricity generation for those sectors account for only about 1/3 of total CO2 emissions. If you want to decarbonize the Indian economy, the manufacturing sector is a good start, but what is extremely important is electricity generation. Electricity generation in India is very, very dirty. So about 70% of the energy sources are fossil fuels, mostly coal. Okay, getting rid of that coal is something very important if you want to really bring down the total carbon emissions of the Indian economy. So overall, I think it's an amazing paper. It has changed my view on the usefulness, sorry to say this here in this room, the usefulness of macro for climate change mitigation. I used to think that climate change mitigation, if you want to work on that, you should do IO. But this paper has actually convinced me that, thinking about firms and firm dynamics and firm modernization is actually very important for that. Two robust contributions, the non-homogeneity at the plant level, and it's actually something that is quantitatively very important. And I think the results are very important for policy. In particular, India loves size-based policies. This is exactly where size matters. So, I look forward to more statements about what we should do in terms of policy or should not do, which is also important. Thank you very much.
Yes.
Super interesting. Thank you. I just have two questions, and you may have mentioned it, but I missed it. One is, I haven't worked with this specific data, but I've worked with very similar data, and I know it tends to miss the smallest firms that you have. So I'm just wondering if I should think about these, have in your results as being about moving firms from like a medium to a large size, or if we could, how we should think about like the smallest firms and moving to medium size. My other question I had was with regards to the prices of all these inputs, so like energy, materials, but also wages potentially, right? Because there's definitely a correlation between the prices firms pay for all this and how they grow. So just wondering a little bit about that. Thank you.
No, those are two awesome questions. So I didn't get the time to show these results, but we also show results. So India also has a survey of informal manufacturing, which is called the NSS. So that's not a panel, so we can't run our main identification strategy, but we produce cross-sectional results that look highly similar to the results in the ASI. So, and we also do kind of the pooled sample that pulls the NSS, so informal, and the ASI is a formal sector, and the cross-sectional elasticity in the pooled sample is similar to the ASI sector. So, again, like this is not exactly our main identification strategy, but we still think that's informative. On relative input prices, so there's really two things. At the macro level, we don't see much going on in response to a change in scale. That is, so we see a little bit of an increase in the wage at the firm level. The price of energy and the price of materials both don't move. That change in the wage is way too small to generate an effect on factor shares like the one we see in the data. At the aggregate level, though, of course, the wage increases with productivity growth. And how much that matters, you could see from the CES line, right? Like this is, why is this line not completely flat in the CES model? Is because the wage increases in GE, but you see that the effect on the energy share is really tiny.
Yeah, I mean, I think we're a little surprised about that. We initially expected to find price effects. I mean, there's great work out there on market power and input markets, for example, but for electricity specifically and for fossil fuel prices, maybe it's because of how regulated the Indian utility sectors are. They really just don't vary at the firm level in this data. So we couldn't find anything there.
Thanks, that's really cool, guys. I was wondering, so you have this cross-sectional fact and then you're taking to the aggregate. And I was just wondering if there are forces that might cause the cross-sectional fact to sort of somehow be divorced from the aggregate. So the one that I was thinking of was perhaps you think you have this fixed cost model, you pay a fixed cost to upgrade to a better barbecue, but that fixed cost, it depends on something like wages or energy prices. So in partial equilibrium, obviously this is going to operate, but in general equilibrium it just wouldn't, because wages would rise in the BGP, and then it's not going to affect firm scale. Likewise, if energy costs are part of that fixed cost. So I was just wondering how to think about that. Thanks.
Yeah, I mean, absolutely. That's why we think the micro to macro aggregation is super important, because you miss in the micro cross section what you get out of TFP growth, which is growth in wages, which would induce substitution towards energy, and that would act to raise the energy intensity. Now, how strong that effect is really depends on the elasticity of substitution between energy and labor. And because we find their complements in the quantitative model, it's actually quite a muted effect. And in addition, wages actually don't grow that much in India over this time. So when we actually match this in our full quantitative growth accounting, there's not a huge substitution effect towards energy quantitatively.
Well, okay, Adrian.
This relates, so great paper. This relates to a few of the questions, and it's probably just me being confused, but could you just clarify how you reconcile the fact that energy over L and energy over K plus L is increasing, energy over value added is falling, and then also when you add intermediates in there, it's still falling, and how to reconcile that with the aggregate trend where it's E over value added. So how do you think about relative prices of K and L, and how does that all add up? Thanks.
I mean, the simple model is really useful there, right? Because this is a model where the energy share is purely proportional to the non-material share. So E over L and E over LK doesn't move. But because the non-material share falls with growth, you have this decline in the aggregate energy share, as well as E over Y and E over value added. I didn't emphasize this because I was running out of time, but energy over value added is really important. What we show is that in a model with intermediates, when you get at the total energy content of output, so direct energy use plus indirect energy use through the whole input-output chain, what you get is that the correct metric to look at is exactly energy over value added. That takes into account the fact that M contains energy and so on and so forth. And so the fact that kind of, well, both in the data and in the model, this is falling tells us that this indirect use of materials isn't undoing the direct effect. Yes, Ishan.
Thanks. Super interesting paper. I was curious, just like a clarifying question about magnitudes. These aggregate graphs, I think there's a big effect from the switch from manufacturing to services. Can't remember whose paper showed that. And so this 50% of the effect, is that 50% within manufacturing? And if so, what is the total contribution of the within manufacturing to the aggregate decline?
I mean, I think this is one point we're going to have to hash this out with Johannes, because we really looked pretty hard for structural change effects. So for example, this is the graph for the aggregate energy decline for the globe, and most of it is within sector, at least from what we could see. This within country sector, I should say. This is Indian energy intensity, and we do see some structural change there within manufacturing. So within, let's say, 4-digit industries. But again, it's not huge. So I think we're going to have to sit down with Johannes and work out exactly where the differences are there.
Very interesting paper and facts. Because I was trying to think about how to square this with what I know about electricity. I know more in Africa than India. I was sort of asking the internet and didn't square it myself. So in Africa, most firms would be getting their energy from the grid or a generator, but so it's electrical energy. So let's just say it's the grid, and let's say that's the only way they get power. The sausage argument doesn't really apply, because it's sort of, you make all the sausages centrally, then everybody plugs in, and it doesn't matter whether you're plugging in from a small firm or a big firm. And so then I was surprised to see the downward sloping patterns. And so I was thinking maybe that's just because India works differently than Africa. It's just much more about making it yourself. It may be related to Daniela's comment. Most firms are under 10. They're probably not sort of pouring fuel into a machine and then you have the glowing molten whatever. Most small firms wouldn't be doing that. They'd be plugging a machine in and using power. So yeah, I'm thinking maybe India is just different. There's just much more self-generation where you literally, like in your model, pour the fuel into a machine and then produce. It may be that I'm thinking mostly of the small guys who are really not doing that. I'm just trying to, yeah, just how do you, in Africa, I think I kind of remember the number being more like 75% of the power, the kilowatt hours, are sort of you buy it directly rather than using the fuel and create it.
So the physical mechanisms would apply similarly with just purchased electricity, right? If you're trying to heat water with an electric boiler, the more water you try to heat, the less energy you're going to use per liter of water. So the mechanisms we have in mind are not about firms generating electricity on site. They happen with electricity too. And similarly for the technological investment channel, a lot of these kind of add-on technologies that reduce energy efficiency are kind of add-on technologies that come, again, take the electric boiler example. A type of technology we have in mind is waste heat recuperation. Think of a big pipe that takes some of the wasted heat and feeds it back into the water you're trying to heat. That's something that adds to a technology that uses purchased electricity and that would improve energy efficiency.
So there's a big fixed cost component in what you're saying.
Yeah.
I mean, that's interesting. I just wouldn't have thought. So there's pretty big increasing returns to scale at the firm level. We should write a different. I should throw out the production functions I'm writing and write a different production function.
One minor point to that. So, a lot of what the firms are doing when you think about these Indian manufacturing technologies is like relatively simple manufacturing, but it's like ceramics, hand tools, foundries. And most of the energy in that is just heating stuff up. And that's where a lot of the losses are.
Okay.
And so we didn't present this, but we actually do a restriction to industries where we're using a lot of energy to heat stuff up, and the coefficient's even stronger. Which
I see.
Is exactly what we expect.
Okay.
Yes.
Yeah, I have a thing that turns out to be quite a follow-up to this. I'm thinking more at the micro level in these plants, and I'm thinking of the job market paper of Emmanuel Murray Leclerc, who's a previous student at Western. So he's looking at the same data with like some of, probably not all the firms that you're looking, but there he highlights a lot that firms seem to vary a lot in their like fuel specific productivity, not energy. Like they all want to produce energy, and some of them want to use diesel, and some of them want to use energy from the grid, and some of them want to use something else. And like they all kind of face the same prices, and they seem to be varying a lot. And so I just don't know, when you do the aggregation, this will imply like a different balance on the productivity loading you're going to get on energy, because it's going to depend on like how the firms actually manage to produce it. And I don't know how that plays a role or not in what you're doing.
No, correct. So there's a lot of like kind of within an industry, there's a lot of variation in fuel shares. I think the important thing for us is like we don't find that projects on scale. When we use our instrument and we look at whether firms change their fuel shares, so like coal versus oil versus electricity in response to demand-induced changes in scale, we don't find anything. So it seems to be like kind of a really interesting aspect of the data that just doesn't project on the story we're telling here. Yes.
So to some extent is like remarkable that you can match your coefficient, the full elasticity, with the two mechanisms you have in mind, right? Which is the physical one and the technological one. Because I would have expected like other mechanisms at play. Like, one is capacity utilization that, at least in this setting in India seems like, very important, right? There is like, you have to turn on the light, you have to turn on a machine, and then if that machine kind of runs full time or not, you're going to have a big effect on like, energy intensity, which also seems kind of consistent with the fact that you don't find much on E over L, because L and capital are like fixed cost or like fixed input, at least in this context. And then the other one, it is like, inefficiencies. Like in this setting, you would expect that like, small firms are very inefficient, just like, waste energy. Sometimes there are like, blackouts, they like, have to start from scratch again. So yeah, how is it possible? Then I guess related to this one, like, what do you think is the external variability, as in like, at which level of scale do you expect this mechanism to like, stop? Does it still apply to the US or like eventually it's like, plateau?
So, on the accounting for the mechanism, I think maybe we're a little glib there, but that holds in the simple model, in the model where there's Cobb-Douglas between energy and labor. When you have complements, you get less. So if you take out elasticity of substitution from the quantitative model, we get something like 60 to 70% of the total effect, which leaves room for all these other things, I think. And then on the external validity, so we want to do this in the US causally. We can't do it because we don't have the census manufacturers. But this, oh yeah, let's get rid of that. Yeah. At least in the cross section, when you look at US firms, you look firm sales and the decline in the energy intensity, you also see a pretty similar cross-sectional relationship. Now, how much is this explaining declines in US energy intensity? Probably a lot less, not because of this, but because the growth in average firm size in the US is much smaller than you see in India, James.
And just if I can add small points on that. So we've tried to look for other stuff, like for instance, as metrics for like how inefficient firms are. We've used the share of like ICT capital in total capital, the share of supervisors in the total workforce, and try to see whether we were getting heterogeneous effects using those characteristics, and we haven't really found anything. This may be for lack of a better proxy vote. Like I don't think we can reject that there's anything going on there. Yes.
I think Pasquale has an answer. I'm going for number 2, so I'll let Pasquale do number. No,
the degrowth thing.
So I guess that one question I had was about the figure that you showed with the technologies and the fixed costs. And I guess like the question I had is when we say that installing this type of machinery entails fixed costs, one has to be careful because a lot of these costs might actually scale with the firm size as well, right? So I guess that's the delta in the theory. So how do we get that the delta is less than 1? I mean, many of these things seem to be scaling with the scale of production.
Yes, so we estimate delta. Okay, we estimate delta using engineering data. So essentially, we gather engineering data on equipment prices by capacity. So we have so this is data from the US, not from India. That type of data doesn't exist for India. But essentially, these are data that are compiled by engineers when they want to do project cost assessments. And so we find in the SEC that it's not similar, but it's well below 1, and that lines up with this engineering estimate very well. So this is one. I skipped this in this time, but it's one of the ingredients to the quantification of this channel.
And a quick follow-up. I guess that for all of this, it's very important to know whether these scaling laws are very stable when we start extrapolating like them orders of magnitude, because we want to say like, oh, as India continues growing, this mechanism is going to reduce emissions by this much. So how stable are they? Like the physical ones that you described seem very stable, but these ones are they also stable as well?
No, we agree. So what we can say on this is like in sample, this seems very stable in the sense that even if you slice the sample by like X anti very large firms, we're getting elasticities that are pretty similar. And they also look like the relationship looks really log linear in the data. I think we have the bin scatter somewhere, but it's just like beautifully log linear. Then on kind of how much do we extrapolate, I think we can bring in 2 data points. One is doing the within sample exercise, take a firm that grows from like the 10th to the 90th percentile of the distribution. Are we predicting a crazy change in the energy share? And we're predicting only like 50% of the P10 to P90 in the energy share distribution. So it's really not like we're predicting crazy changes. In the time series, what we're predicting for India in terms of the energy share in 2050 is not even at the level that the US has today. So also in the time series, it doesn't seem like we're extrapolating like crazy. But fair point, like this non-homotic CS with a constant elasticity implies that in the very, very long run, the energy share goes to 0. So that's...
So we don't have to limit them. I'm joking.
There was a second question.
Michael, go ahead.
Yeah, as you can imagine, I need to follow up on the structural change stuff. So I would have also thought that, as you go towards intangible inputs, services, and so on, the energy intensity falls. And when we did the cross industry, cross country, we found pretty strong evidence. And you're saying in India that's not the case?
Yeah, so we've looked also. We were very surprised too. So what happens in India is that the most energy intensive is really manufacturing, and the manufacturing share is pretty flat. Agriculture is falling, and services, including transportation services, are rising. And it turns out that the kind of average intensity of services, including the transport bit, is kind of the same as the energy intensity of agriculture. So these two things are sort of canceling each other out.
Okay, so that's actually interesting because I guess you might say, you know, if transport is like, if you need to transport the agricultural goods, right? So I guess if you were to do sort of the input-output tables for the final products, the association might be like slightly different, right?
Yes,
Okay.
so we haven't
done that. I mean,
Yeah.
there are also scaling laws for transport as
Yeah.
well, so we think about that, but we
Yeah.
haven't done that.
Okay, no, that's interesting. Thank you.
I don't know if we have time for David's question.
No, I-
David can get a second.
Go, David. No, I,
Not even
okay.
years of work.
No, so I was looking at your figure 6, but you still get, even in the US at $100 million, there's still this energy intensity. And I'm just trying to, I was asking Tommaso and his guys, and then Tillman has a paper about sort of getting this. I would have just thought that happens very early on in the production. So I would have thought $100 million is no more scale. I mean, you're sort of just picking the inputs, and you're pretty close to optimal. Figure 3.6, you have a lot of cool stuff. I couldn't quite tell how much 500,000 rupees is. Yeah, like, is that about a scale economy from 100 to 250 million US dollars in sales?
So in the US, I know of one other paper that has looked at this and talks about heating as well. So, you know, I think on the US, like, the fair thing is we can say much less. This comes from the publicly available version of the Manufacturing Energy Consumption Survey, which is tabulated data. If you believe in these physical mechanisms, and if you believe that there's still, like, you know, okay, maybe one interesting data point is combined heat and steam generation. That is really a game changer for energy intensity. In the US, the penetration is still super low and rises very steeply with size.
Okay.
So it seems that, you know, as long as you have these very high fixed cost technologies that are really important for energy intensity and that even small US firms struggle to adopt,
Yeah.
you can kind of rationalize.
Yeah, I mean, it might not be for this paper, but we've certainly got an ambition to see how general this is and take it to the US. So if anyone's got the manufacturing census and wants to put us on the project, come talk to us.
Great.
All right, yeah, you can find co-authors for the next coffee break. See you guys.
But at a very small scale, right?
Let me open my mail.
Are we not moving on? I thought the next presentation was at 4:54. The agenda doesn't say we have a break.
Finally, now we.
You're all kind of getting.
Now that he's already.
Buy a grain mill that's that big. If you're gonna do grain milling, you have to have sort of buy one that costs $1,000, and you maybe, or you buy a boiler that's like, you're not
Good. Okay, so last session for today. Very happy to have Martin, Lost in Transition. Go ahead, 20 minutes.
Thank you very much. Thanks so much for the to the organizers for putting this paper on the program, and thanks for organizing a really great edition. This is joint work with Philippe, Antonin, and John, who I'm told are all supporting me via YouTube. So exactly. So ask them any questions, but don't expect their response. This paper is about technological transitions, and in particular about what happens if something goes wrong in the middle of one. Now, the starting point of the paper is that advanced economies are constantly reshaped by transitions from mature to emerging technologies. Think of the transition from typewriters to computers, from steam to electricity, or from combustion engines to electric vehicles. Now, the source of the start of a transition can be diverse. It can be ignited by, say, a general purpose innovation, could be driven by changing consumer preferences, or in the theme of the last few papers, it could be changed by policies, say, the implementation or the expectation of, say, a change in carbon taxes triggering a green transition. But for these transitions to materialize, you need a stream of complementary innovations. In the case of the green transition, we hope we're going to come up with ways of producing everything that we currently consume and then some in a less polluting ways. So that naturally raises the concern that if there is a disruption to those complementary innovations, that can slow down the transition. And the particular disruption that we have in mind in this paper is a financial crisis. A financial crisis affects a firm's incentives and ability to invest in innovation. And if that happens in the middle of a transition, that can be particularly costly because it's hurting the technology that's on the rise. To give you the main motivation of the paper, let me plot what happened to green technology around the global financial crisis, one of the big shocks of our time. So green technology was very much on the rise in the years prior to the global financial crisis. This plot shows that. This is OECD patenting in what the OECD calls green technology, which is a broad definition that includes things like climate change mitigation. So examples of green patenting by this classification includes things like LED lights. If we have Germans in the room, it also includes things like nuclear energy. And these patents were very much on the rise prior to the global financial crisis. They went to something like 4 to 11% of patents, but then after the global financial crisis, there was a real slowdown in the share of all patents that was related to green technology. Now, what we're going to argue in this paper is that that is actually a broader feature of emerging technologies. Also, if you look at more, if you look at more particular technologies. So one example here is agricultural patents. So here we're comparing mature technology in agriculture, so things like plows, or innovation in things like pesticides, those are conventional agricultural technologies, versus the fraction of patents that is related to plant genetic engineering, which is what more of the recent agricultural patents were in. You see the same thing. There's a rise before the global financial crisis, and then that slowed down. And you see the same if you look at, say, electric vehicles versus internal combustion engines. You see it for things like coherent optic fiber versus more traditional measures of transmission. On average, we find that emerging technologies saw their patenting rates decline around the crisis. Now, the question that we ask in this paper is, do financial shocks disproportionately harm innovation in emerging technologies? And we're going to argue that that happens even if there is no intrinsic ability different in firms' ability to finance innovation in mature or emerging technology. Now, we're going to build that argument on two assumptions. The first assumption, and I think this is really uncontroversial, is that young firms are more financially constrained than old firms. In the model that I'm going to present you, we're effectively going to hard code that, and people in finance are pretty comfortable with this. The second assumption is that innovation is directed and path dependent. And by that, I mean that firms build up expertise in the kind of technologies that they've innovated in before. But a kind of world that I'd like you to think about is think we're starting from a steady state in which there is a mature technology that dominates. So firms in the 1980s could try to innovate in generative AI, but it was just really costly. Followed by some transition shock that makes it possible or profitable to innovate in an emerging technology. At the start of such a transition, young firms are going to endogenously have a comparative advantage in innovation in the new technology. And that's because they don't have the track record yet in a technology that's already mature. So that means that at the early phases of a transition, the young firms are going to be doing a disproportionate share of the innovation in the new technology. But young firms are the ones that are more financially constrained. So a financial crisis is going to harm new technologies more because of the identity of the firms that self-select into the innovation in the emerging technologies. So the bigger lesson of this paper is that a tightening of financial conditions is particularly costly when the economy is going to a transition to new technology. I don't think I say anything new here to people in the room when I say that financial crises are costly. But the point of this paper is that there's a state-dependent effect of financial crises. When you're in the middle of a big technological transition, because of the identity of firms that are driving that transition, a crisis is more costly. We do a bunch of things in the paper. It's a short talk today, so I won't go through all of them. In particular, I'm going to skip the motivating facts. And the motivating facts that we show in the paper is that young firms innovate disproportionately in young technologies, and young firms reduce their innovation during the global financial crisis. And we showed that patenting rates in young technologies fell further behind trends than mature technologies around the crisis. What I am going to go through is the theoretical analysis. I'm going to present a Schumpeterian growth model with emerging and mature technologies, path dependence in innovation at the firm level, as well as financial constraints. And then I'm going to explain that that financial crises have a state-dependent effects on emerging technologies in such a model. Then we're going to apply the framework to green innovation around the global financial crisis. I'm going to first present you some micro data from a small sample of German firms to show that firms that were more exposed to the global financial crisis reduced their green innovation, but not their non-green innovation. And then in turn, I'm going to show you that that overall effect is entirely driven by a composition effect. I'm going to show you that young firms cut everything, and young firms were just responsible for a large share of green innovation before the crisis, exactly as the model predicted. Then we're going to quantify based on the microdata to see whether that mechanism that I just outlined, that intuition, actually has some quantitative bites. And I'm going to show you that the theory that I outlined can explain most of this slowdown in green patenting around the crisis. In the interest of time, I'm going to skip the literature review, but if there's any questions about contribution, I'm happy to elaborate on that after the talk. Let me start with the model. So the model builds very much on Cladocortum. It's going to be a model where households are really simple. They derive log utility from consumption and they supply their labor inelastically. There's a continuum of goods in the economy which are indexed by J, and firms which are indexed by I produce one or multiple of these goods. Now, each good in the economy can be produced either with a modern vintage or an old vintage of technology. I'll tell you in a moment what that means for the production function, but for now, just take that as given. And firms can produce any good that they own a patent for, and a patent is going to be particular to a technology. So the patent enables you to produce either with the modern technology or with the previous technology. Other than that, a patent grants a firm I the right to produce a good J at some level of quality Qij, and the level of quality enters in the aggregator like this. So this is GDP. Here we have the aggregator over the goods J in the economy. And within the aggregator here, we just have the sum of outputs. So there's perfect goods within a particular product are all perfect substitutes regardless of who produced them. The set capital I is a set of firms that can produce good J. And this is the level of quality at which they produce them, with the technology H being either the old or the modern technology. So quality just raises the amount of utility that the household gets from consuming a unit of a good, and the higher the level of quality, the more attractive the good is to consumers. Now, potentially multiple firms can produce good J, but firms compete à la Bertrand. So in equilibrium, there's only going to be one firm producing, and that's going to be the firm that delivers the highest quality over price. So as I told you, there's two technologies, a modern and an old one. So what are they? Well, say a firm I produces a good J with the old technology. It just has a simple linear production function in labor where we've produced the productivity of producing with the old technology to 1. If a firm produces with the modern technology, it has a very similar production function, but it has a different relative productivity. So that's the only difference between these two technologies. And the way that you should think about this productivity is it's going to be below 1 in some old steady state. It's going to be above 1 in some new steady state. So if you wanted to use generative AI in the 1970s to produce, the relative productivity would just be really low, right? It could even be 0 if you want it to be. That then affects the marginal cost of producing with either of these goods. So the marginal cost of producing with the mature technology is just the wage, because this is labor, and with the modern technology, you're going to have wage divided by that relative productivity. Now, let me go to the key assumptions of the framework. The first is about how innovation works. So firms can expand their portfolio of patents. Thank you. They can expand their portfolio of patents by choosing the Poisson arrival rate of patents using either the modern or the old technology. So firms are going to spend money on R&D to raise both. Now that's directed, so you choose separately how much is spent on R&D with either of these. And if you're successful at innovation, a firm is going to raise the level of quality at which a particular product can be produced by some step size lambda. Now, the first key assumption is that these innovation costs are going to decline in the stock of products that a firm already has in the directed technology. So if you have a lot of experience coming up with patents in the directed technology, you become relatively good at producing that, at developing more patents with that. So how do we model that? Well, the total R&D bill of the firm is going to be a function of the Poisson arrival rate of patents in the modern technology or patents in the old technology. But then there's this term here, N, and this is your experience with the technology. And so this psi, I'm a bit dyslexic with Greek letters, but I think this is a psi, or is it chai? Hey guys, I did warn you, right? So this thing is greater than 1, right? So the higher your N, the lower the cost of achieving a particular Poisson arrival rate. And this cost consists of 2 components. It consists of the number of products that you already have in that technology. And then there's some baseline productivity. So any firm, even if you've never innovated, can potentially innovate in the modern technology or the old technology. And an entrant, in that sense, is just going to be a firm that has no experience, right, in the technology. And there's some overall convexity in these costs. So that's going to mean that if a firm has a track record of successful innovation in the modern technology, it chooses to dedicate more of its R&D resources to that. So think of that convexity as reflecting some span of control. The second key assumption is going to be on the financing side. We're going to have a very simple model of financing. So we're just going to assume that the maximum amount that a firm can spend on R&D is going to be some multiple of its revenue. And that multiple is going to improve as a firm gets older. So how do we do that? So this is the maximum amount that the firm gets to spend on R&D. This is its revenue, which depends on how many products you have, how much customers like them. Then there is a time fixed effect. This is later on how we're going to introduce a financial crisis. So a financial crisis is going to be a reduction in big theta. And small theta is the firm level measure of its financial constraints. Now, the key assumption is going to be that over time, your theta, your small theta, is likely to improve. So theta improves with a Poisson arrival rate nu up. It's going to decrease with some Poisson arrival rate nu down. And the key assumption is that the probability that it improves over time is going to be greater than the probability that it weakens. You could microfound this. You could say firms are meeting new banks and are losing old lending relationships at a lower rate. We're not going to do that. We're just going to hard code this relationship, and we're going to calibrate the difference between these two to match how the effect of a tightening of credit weakens with firm age. Those are going to be the 2 assumptions that we need for everything to hold. There's a bunch of stuff that I'm gonna skip. I just wanted to say how exit and entry works. So like in any model of creative destruction, if other firms come up with better versions of products that you're the market leader in, you stop producing them, you exit the economy if you stop producing your last product. And the economy grows because of that process of creative destruction. Let me get to the key bits. There's two ways that firms optimize in this model. There's static optimization, which involves firms choosing the optimal price that they charge for each of their products. And there's dynamic optimization, which is firms' R&D. Now, the key stuff is here. Because we have a Cobb-Douglas aggregator, firms are going to limit price their closest competitor. And that means that if I am producing with the modern technology and the previous producer is producing with the old technology, my markup is going to be the quality difference between the two firms multiplied by our relative productivity. Vice versa, if I'm producing with the old technology and my closest competitor is producing with the modern technology, my markup is my quality difference divided by my cost, the cost differential. If both producers have the same technology, the markup is just pinned down by that quality improvement. The more important bit is the dynamic optimization. So this is the arrival rate that firms choose of either these modern or these old patents. They're going to be a function of how valuable it is to own a patent in either direction. It's also going to be a function of your financing costs. So this curly M here is the shadow price of your financing. So this is going to be 0 for firms that are not financially constrained because they've outgrown that, but it's going to be positive for firms that have not. And this N here is that experience variable that I talked about earlier. So if there is a big incentive to invest in, say, the modern technology, but you don't have much experience, your overall possible arrival rate is just going to be lower because it's more expensive for you to develop those patents. Now, let me outline the key idea of the exercise we're going to run in a moment. What we're going to do is look at a change in the relative productivity of the modern technology. So AM is going to increase. Say Gen AI becomes feasible to use in production. That's going to raise the markup of firms that use that technology in their patents. It's going to reduce the markup of firms that do not. As a result, the value of getting one of these patents increases. But initially, firms that have no experience in those technologies are going to choose fairly low arrival rates. That means that early in the transition, young firms are going to do a disproportionate share of the innovation in the new technologies, but young firms are also the ones that will suffer the most if there's an aggregate tightening of financial constraint to that capital theta that I just mentioned. The model is GE and the likes. If you want any details of that, have a look at the draft. The last few minutes, let me quickly explain how we discipline and test the framework. We're going to use differential exposure of firms to the global financial crisis to test the mechanisms of the model. And in particular, we're going to use a small sample of German firms from Kilian Huber's exercise, where he compares the effect of being exposed to Commerzbank, which is a German bank that cut its corporate lending portfolio after losses in its American subprime loans. We're going to look at the differential effect of that on green patents and non-green patents. So we're going to run a simple PPML where we say year by year, what's the effect of being tied to this bad bank in 2006 on your patenting around the global financial crisis. And this is what we find. Commerzbank reduces its lending between 2009 and 2012. And what we see is with somewhat of a lag, there's a reduction in green patenting, right? So there's a lag here, but there's a sizable reduction in green patenting, not in non-green patenting. If you add more controls to this, like 3-digit industry fixed effects interacted with the year, the lag changes a bit, but it doesn't affect the overall negative effect over time, right? So we see that firms cut their green patenting if they're hit by Commerzbank, not their non-green patenting. That in turn turns out to be driven by a composition effect. So what happens in our model? In our model, if firms are subject to a tightening of financial constraints, it raises that shadow price of financing, and firms are going to cut everything based on how exposed they are to the shock. That means that in our model, young firms cut all of their innovation, older firms cut nothing. Now we can test that. We can do a triple diff and diff. We can look at firms with high exposure to Commerzbank and that are below median age and see what they do. Now, this is the overall effect that I just showed you, right? There's a negative effect of green patenting on Commerzbank exposure, and there's no effect on non-green patenting. But if we split that, we actually see that young firms cut everything. They cut their green patenting and their non-green patenting, whereas the older firms cut nothing. In fact, we get a positive coefficient on green patenting. And that's exactly what the model predicts, right? The model predicts that these firms cut everything, and the reason that you then get that overall disproportionate effect on the green patenting is because that's what the young firms tend to do. And that's exactly what we find in the data. So the young firms are responsible for almost half of all green patenting prior to the crisis, and they're responsible for a much smaller section of the non-green patenting. So that together gives that triple different diff that I just showed you. Okay, so then we quantify the model to match what I just showed, where we're going to think of the modern technology as clean technology and the old technology as say the dirty technology. And we're going to see, does that mechanism that I just outlined of young firms self-selecting into an emerging technology, green technology, explain why you see green patenting fall around the global financial crisis. So the exercise that we're going to do is we're going to calibrate the model to match pre-1995 moments in Germany. Then we're going to see what happens in a transition. So Michael tells me I'm already out of time. Fortunately, I've just got 2 pretty graphs and then we're done. So here is what happens in the economy if we have a financial crisis. And this is the share, this is the index of the share of all patents that's green. So what you see is this is the initial path. The model predicts that if we put in the tightening of credit supply that we saw in Europe, you get a full flatlining of green patenting. So this model really has power to explain a sizable reduction in green innovation purely through the self-selection of firms into that technology. Final graph that I want to show you just to bring home the mechanism that I outlined is what if the same financial crisis had happened 5 years later? This is the impulse response, so it's the difference between these two lines. So this is the impulse response if the crisis happens 10 years after the start of the transition, so in 2008. Now let's say we have the same tightening of financial conditions 5 years down the road. Well, in that case, the model predicts a much smaller effect of the crisis on green patenting. And that's because the financially constrained firms are driving a smaller part of the overall green patenting, right? And that's the key message. These shocks, particularly bad in the middle of a transition. Thank you.
Thank you. And the discussant is Pablo Kurlat.
Hey, thanks for having me. I don't have much to say. Very good. All right, let's just use it this way. Okay, so the argument in the paper is as follows. Young firms specialize, is this catching me? Yeah, okay. So young firms specialize in new technology. In the model, the reason why that's true is that the cost of innovating is lower if you're already producing that sort of stuff. And then young firms are more sensitive to financial conditions. In the model, that's because how much innovation you can pay for is proportional to how much revenue you're making. And then when you have a financial crisis, that leads to less innovation in new technologies and possibly in green technologies as an example of that. So that's the idea in the paper. Now, I'm not a huge expert on the economics of innovation. So what I'm going to do is I'm going to sort of have the discussion at the level of the stuff that we all know about, which is what we learn in the first year of the PhD. Now, Alessandro and Kian, they learned all sorts of interesting stuff in the first year of their PhD. Whereas Pasquale and I, what we learned in the first year of the PhD is we learned a little bit of basic arithmetic from Daron. We learned about colors and shapes from Ricardo. And then we learned a little bit about how to make friends from Ivan. So that's what my comments are going to be about. So let's start with a bit of arithmetic. So let's forget about equilibrium, forget about optimization. And let's imagine that the way the world works is young firms, they always work on a technology of age AY, and old firms always work on a technology of age A0. And that's fixed and it doesn't respond to incentives or anything like that. And then the share of young firms that are doing innovation falls from 40% to 33%, which is the figures in the paper. By how much is the age of the technology on which we're innovating going to change? That's a calculation that's not in the paper, but you can sort of reconstruct it from what's in the paper. So this is a figure that Martin didn't show, but it's in the paper, which shows a relationship between the age of technology and the fraction of that that's being done by young firms. So what you can do is, and this is the wrong thing to do, by the way, you can go from 40% to 33% and see how much technology ages. And that's the wrong thing to do because the axes are the wrong way around, and this has a base scatter. So in order to reconstruct the calculation that I want to do, the first thing you have to do is to undo the bin scatter. And this is, I got the data from the authors. So first you undo the bin scatter, then you reverse the axis, and not the other way around. And this is the slope that you get if you run the reverse regression, which is how old is the technology as a function of the age of the people doing it. So then if you extrapolate to the ends of the axis, then young firms are doing technologies that are 80 years old firms are innovating in technologies that are 33 years old. So that's the numbers you can plug in. If you plug in those numbers, then before the crisis, the typical innovation is done on a technology that's 27 years old. And after the crisis, typical innovation is done on technology that's 28 years old. So it's like a year older. Whether you think a year is a big number or a small number, I don't know, but that's what the evidence in the paper points to, and it's there. Okay, so how does that account for the whole thing? Does that account for how older the technologies are after the crisis? That is something that I think you could compute directly in the data from the paper, but I didn't come up with that in time to ask them for the data. So I sort of reconstructed from what they do report, which is a little bit different. So they report this, which is project the life cycle of any given technology and try to guess how much innovation in that technology is going to happen, and then see the difference between that and what actually happened after the crisis. So that's this plot. So this is young technologies relative to old technologies, how much lower they are. And this is like 0.5 log points for like 40% low. So if you then say, oh, young technologies fall 40% relative to old technologies, we have to think, to convert that into years, you have to say, well, how old are the old technologies? How old are the young technologies? And if you sort of do your best to put numbers on that, which is something you could directly do in the data instead of doing all of this indirect stuff that I'm doing, it looks like the average age of innovation in the data goes up by something like 2 years. Now, there's a bit of uncertainty around that number, and I'm sure if you did it exactly, maybe it's not exactly 2, but you're getting at least half and maybe perhaps more just from the fact that the firms doing innovation get older. So that's there, and it's a big chunk of what's going on. Now, one thing that is a little bit, I'm not sure what to make of it, is if you then go to their simulations in the model, once they calibrate, and they say, okay, the transition gets delayed, and this is a graph that Martin showed at the end, the transition sort of gets delayed by something like 4 years. Now, I'm not sure exactly how you go from, well, the technologies you're working on are 1 or 2 years older to the transition gets delayed by 4 years. My conjecture is that there's something in the way they do the empirics where they sometimes have continuous variables and sometimes they have discrete variables. Like in the model, it's discrete. It's either the old or the new technology. In the data, these are all continuous, and there might be something in the conversion between continuous variables and these discrete categories that is maybe interfering with the quantification. That's just a conjecture. I'm not sure if that's the reason. My suggestion would be to do everything with continuous variables, both in the model and in the empirics. Okay, so that's arithmetic. Now let's do colors. So my interpretation of the paper is that this whole discussion of the green technology is a bit of a red herring. The paper is really about new technologies, and green technologies are just an example of technologies that are relatively new. Now, of course, I get it. You know, climate change is an important thing. We might get crocodiles in the North Pole, so we definitely care about this. But it's not really the idea that's sort of in the paper is not really about green technology. It's about new technology. And green is sort of correlated with new. So but since you can measure newness directly, I think that's sort of preferable. And also the financial crisis may have interfered with green technologies, but it could also have interfered with all sorts of these other technologies that, according to my friend Claude, were sort of new in 2007. And Martin mentioned some of these. So I would maybe focus less on green and focus on new technologies as the key thing to think about. And so the question I would ask is, how much is the slowdown of innovation in new technologies can we explain with the model? That's sort of the question that seems more interesting to me. So examples of this. So this is the table that Martin showed at the end, where, so by exposure to Commerzbank, you say, well, age accounts for the entire fall in green innovation. The way I would like to see this table is first continuous measures instead of binary. That seems easy to do. And then I would forget about green and focus on tech and the technology age and ask, is it that innovation by young firms is more sensitive to Commerzbank? And then is innovation of young technologies more hurt by exposure to Commerzbank? And the hypothesis would be that once you take into account the age of the firms doing it, this effect is zero. And that's something I would like to see. Also, you could do the same thing instead of with the identification through Commerzbank, just in the time series. Suppose you say, what's the flow of patents over time by age and by age of technology and by age of the firm doing it? And again, you would imagine that if you do by age of the firm doing it, you find an effect over time. If you do by age of the technology, you only find it if you don't control for the age of the firm doing it. So that's something that seems eminently doable, and it'd be interesting to see if it's there. All right, so that's colors. Let's do shapes. So two shapes that I know about are horizontal and vertical. So here's how innovation works in the model. There's all of these varieties, and they all start at some technology level. And then there's this sort of quality ladder type thing. And some technologies have a jump, some don't. And the jump can be a brown jump or a green jump, depending on if you're doing the modern version of this or the old version. And over time, you get all of these sort of jumps. And as the transition takes place, more and more of these jumps look green, because that's the new technology that attracts, because it's more productive, it attracts more and more of the innovation. So at the end of the transition, you're going to have mostly green, where you had mostly brown at the beginning. And it's all vertical. Yeah? So all of it's like a many quality ladders type of model. So this is a model that is well suited for thinking about a one-time transition from the brown technology to the green technology, which is, of course, what the paper is trying to do. But it makes some things hard to capture. For instance, the idea that there's always some new technology arising is something that this model is not really designed to do, because it's you start from the brown, you end up in the green, and then you're sort of done. This idea is sort of there, but not quite. But I think it's an important one, that new technologies don't immediately displace old technologies. The way it works here is that each time there's a jump, so here to here, this is like the electric car, and it just got better, and it completely displaced internal combustion engine cars. But then there's a new development, which could be a slightly better internal combustion engine car. It completely displaces the electric car, and back and forth, because it's perfect substitutes. Now, I think the idea that there's innovation going on in technologies that are very old, I think it's a really interesting idea, and I think it's worth retaining that. But I would like to see it in a way that allows in the model the possibility that there's always new technologies coming up. So maybe something that allows sort of horizontal innovation, where you come up with new varieties, and there's like tons of models of that, which you all know better than I do. I'd be sort of interesting to see if there's a way to incorporate that doesn't make the model unwieldy. I would find that interesting. So there's some things that are kind of awkward that come from just doing this vertical thing. So in the model, when you calibrate it, there's a tight connection between the size of the innovation jump and the markup, which seems, you could imagine tons of reasons why that would not be the case. And if you have like allow for a more complex pattern of substitution among goods, you could relax that. I don't know if that's sort of feasible within not making the model unwieldy, but if it's feasible, I sort of be interested in that. So that's shapes. So let's talk about making friends. So there's a function which Martin also showed. There's a cost of developing innovation. So these X variables are the flow of innovation. This is the cost of obtaining this sort of Poisson flow of innovations. And it's a function of how much stuff you're already doing. I think this is really interesting because this is the theory of the firm, which in a lot of these models of like innovation with firm dynamics and so on, they are not always very explicit about why firms exist and why they're there. And I think that's a really important thing to think about. And this paper has a theory of the firm. In this paper, and they say it like existing production activities generate organizational capital that facilitates further innovation. So this is the people doing the production are friends with the people doing the R&D for that same firm. They're talking to each other. They're telling each other what problems they're encountering in a way that's not mediated by markets. And that is, I think, a really important idea that this paper, it's sort of in the background, but I think it's important because there's all sorts of things that you could do in terms of innovation, even innovation policy, where if you don't understand what firms are, you might not be able to judge whether those policies are a good idea. Let me give you an example. Suppose we do a temporary subsidy for production of electric cars, yeah? And it's temporary. So in some models, if it's temporary, people do the present value of the subsidy. It's sort of, by the time I come up with the innovation, the subsidy is gone, not worth doing. On the other hand, if in a model where the people producing the cars are talking to the R&D people, if you force them to produce cars to take advantage of the subsidy, you might get innovation out of that. Similarly, should we direct R&D subsidies to incumbents or startups? Well, depending on what these firms are, that might make a difference. And I think there's something really interesting in the way that this is modeled, where it has a theory of the firm, a plausible one at that, which I think is worth thinking more about. So that's it. That's about my comments.
Please, Chen.
So how to think about equity financing? Because I think a defining feature of those type of new technologies is more risky. So that's why I think it's you see VCs, Ps, which are more like equity financing. And I think in particular, I think for your context, first, if my understanding correct, it's kind of the model was like debt financing instead of equity financing. And also in the context of mapping to the data, I think Germany is a context in which like the substitution to equity financing from like a bank shock is pretty limited. But if you do the same shock in US, I think probably you can just easily substitute towards equity financing.
Yeah, I think that's a good point. I mean, the key ingredients, right, for this mechanism to hold is twofold. So one is you need young firms to be more financially constrained than old firms. And second, you need that degree of path dependence in R&D. Now, where equity, I think, does not make a huge difference is exactly in the fact that young firms are more financially constrained, right? Especially because as firms age, their access to equity markets actually improves. So I think qualitatively that doesn't alter the narrative that I just outlined. You're absolutely right that our quantitative exercise, where the question is this qualitative story that I just told you about, does that have any bite, is based on Germany. And Germany is especially a country where there is a limited ability of firms to substitute. I think where that really matters though is it gives us a good diff and diff, right? So the reason that we have this firm level experiment where we compare firms with high exposure to Commerzbank and low exposure to Commerzbank is not because we think bank financing is per se the most relevant source of funding for firms. It's if you want to test a mechanism for a model like this, you need to have a differential exposure of firms to that global financial crisis, and banks are just such a good way to do that, right? So I think the German data really enables us to say, does this qualitative story that I just outlined, one, bear out in the data, and two, I agree, for a particular country, for a particular technology, where's Pablo? For a particular technology, right, green technology, and the answer there seems to be yes. But I 100% agree that in a country with more developed equity markets, or certainly anywhere where the age access to finance relationship is different, the quantitative results are going to look very different. And I forgot to say, Pablo, thanks very much for the comments, which I'm not allowed to respond to. But yeah, Joe.
Well, unless we elevate them, but. Thanks, Martin. Very nice paper. So I actually had a reaction that was related to Pablo's. That means you can respond to it, which is I wondered if this paper is in part about these Reinhardt-Rogoff facts. You know, the financial crisis happens. There's a very slow recovery. It's associated with this, or, you know, the Jordan-Schiller-Octavio facts. It's associated with quite a long TFP slowdown. Seems to me this might be the heart of it. I guess I didn't see too many theories explaining that well. And yeah.
Yeah, I think that's a great point. I think if you look at the global financial crisis, it led to a really protracted reduction in potential output growth. There's some in an endogenous growth model, you very easily get that, right? And we saw Ufuk present that as well. I think the challenge, I think, is Joran still here? So hey, if you look at around the global financial crisis, if you look at just the macro level of R&D, didn't really dent, right? So overall R&D intensity hardly fell, and the absolute level of R&D fell by what, like 10-15%. So if you think that the incidence of those R&D cuts is random across all innovations in the economy, it's really hard to get any sort of meaningful hysteresis out of that exercise. So those reductions in innovative investments really have to hit the kind of innovations that we care about, right? And what this paper offers you is a theory where, because the firms that are going to be the ones cutting their innovations are the ones driving the thing that the long run growth is going to come from, you're going to get a bigger overall effect in the long run of a financial crisis than you would get if you would put some sort of disruption in an AK model. So I think that's a great point. You're going to tell me I missummarized your paper?
No, I wanted to ask you because Diego Kensick and friends have this paper, Green Business Cycle, that shows green innovation is countercyclical, which sounds like the opposite here. And for a second, I actually thought you were on that paper, and it was confused. So what do you make of that evidence?
So I think in general, the mechanisms that we outline are really specific to financial shocks and not necessarily to business cycle shocks. Is Diego still here?
No, he needs to present in some other session.
He's presenting next door. So the motivating empirical evidence in their paper shows that in response to a monetary policy shock, green innovation falls less than non-green innovation. That we actually ran that similar regression, and we certainly find that actually in Europe, green innovation falls more than non-green innovation after a financial shock. There's a few differences in methodology, so they're using different monetary policy shocks. They're detrending in a different way, so we're not really detrending the series when we do that. We include like year fixed effects or something. So we didn't quite find those same patterns in the European data, but your instinct is right that if in our model the source of the tightening of financial crisis would be a monetary policy shock, you would get that the green innovation falls more than the non-green innovation, as they said. Diego and I have agreed at some point we're going to sit together and find out exactly what explains the difference between those two.
And what if you run like impulse response on, say, the excess bond premium shock, like which maybe Mark and others have done, as a proxy for financial shock? I wonder what you get from that.
Right. Yeah, we could do that. Yeah. Thank you. I think Pasquale was first. Sorry, Pasquale.
So I guess going back to the adding up point, which we learned to add during first year grad school. So I guess that when you said it's small firms, my first intuition was, well, they're small. They surely account for a small share of innovation and for a small share of patenting. But maybe the relevant question is not necessarily like what share of innovations being done by a small firm is green or blue or old or whatever, but conditional on an innovation being young, what is the probability that it comes from a young firm as well, right? I guess that was the change in access that Pablo was doing. And I think reporting that object would be very interesting in the paper. So of the portfolio of all green innovations, what share is coming from small firms? And that should be a big number or a number bigger than the share of small firms in the economy.
Absolutely. So I'm not sure if I can still show you. So for green, I actually showed you this, but I went really fast at the end. So so for overall young technologies, this is in the paper and it's based on the data that Pablo just showed. But this is the one that you're asking for now. So this is the fraction of all green patents that comes from the younger half of firms, and this is the fraction of all the non-green patents, right? So that's exactly what the model predicts. After the global financial crisis, with exactly the same lag as when we find the diff and diff, that collapses, right? So when I started talking to people about this paper, one of the comments I get was actually, the real green innovators, they're actually companies like ExxonMobil, and you have to ask yourself why, right? So first of all, ExxonMobil has become a green innovator recently, right? When the younger firms retracted. We also have to ask, is ExxonMobil a company with a comparative advantage in green innovation, or is it a company that has the money, right? And what really makes a difference in our paper is the young firms are financially constrained and therefore they can't fully leverage their comparative advantage in green technology. If there's one correction that I can make to the question, so you were talking about small firms. So in this framework, there's a really big, there's young firms, exactly, right? So, and if we do the diff and diff with young versus large firms, we actually don't find that triple diff. So there's really something special about young firms, and we think it's the financial constraints. I think Connor was first.
I had the same question as Joe. I think it's super interesting. Like, so Reiner and Rogoff would say that financial crises are different because somehow they lead to permanent output losses. And I wonder if focusing on the green transition is underselling it a little bit. Maybe this is always happening. We're always transitioning to new technologies and young firms are the ones doing it. And I think one way to check that would be to say, well, let's look at other financial crises like the Great Depression, patenting, or maybe Japan in the 1990s, and say, do you see exactly the same thing going on? And then maybe you've resolved this puzzle.
Absolutely. I think that's a great point. So we do a version of this in the paper, actually. So what we show for the global financial crisis, but I'm going to tell you that it generalizes. So what we show for the global financial crisis is that if you estimate a pattern of how much firms are how much if you estimate a trend per technology of how much patenting there's going to be, and you look at how much actual patenting deviates from that, what you get is that the younger the technology, the bigger the post-crisis deviation. Now you can run that regression basically from every year between now and the 1970s. And what we find is exactly at times where Chicago Fed's index of the tightness of financial crisis, whenever that index worsens, we find that innovation in younger patents falls further behind trend in subsequent years. We see exactly that more general pattern that you outlined. Yeah, I think Sarah was sorry.
Oh, so a very similar point on green versus a dirty technology. Let's think that if we're looking at new versus old, and I have done this work where we look at the impact of financial. Also similar, a bank using the same variation, although with multiple banks for the US. And what you will see is that even for incumbent firms, they do way more incremental innovation, and where they cut is on radical innovation. And radical as meaning as, going to like different type of product categories, which is, I feel like it's it doesn't have as much, although we did look at the age as well, and there was a additional effect, but we will still see in incumbent firms this, in an environment where they are financially constrained, again, just in that, the same period, that they were cut on radical innovation, also among incumbents.
Right, great. Thank you.
Yeah, so I have maybe a question about all this.
I had this in the models we write down. These things are really costly because you don't make you don't make an investment this period, and that resource completely lies idle. My view of the world is this like a stock flow type of thing. Yeah, maybe those ideas are accumulating, and I'm going to snap right back once the financial crisis is passed. So maybe it might be good to see if in the data that my view is rejected, because that's crucial to kind of getting this Reinhard-Rogoff type of effect, that that lost time is actually significantly costly. It's not just going to snap right back after that. And maybe you have the data to see.
I think it's a great point. So there's a parameter that disciplines the extent to which that happens in the model, and it's the overall convexity of R&D costs. And I think out of the parameters that were whether we say it out loud or not, out of the parameters that we're a bit nervous about, I think this is actually one that we're not that nervous about, because it's one that can be disciplined with the cost elasticity of R&D. And from discontinuities in tax schedules, there's an industry of people estimating those, and we're choosing a very standard value for that convexity. But you're absolutely right that the closer you make that parameter to linear, or Nikos, the more there's going to be a bounce back to trend. Yeah.
So related to like Sarah's point before, I kind of would have thought that like more radical or like younger technologies are riskier, and so then potentially we just like redirect innovation towards like less risky technology during a financial crisis. But it seems that you don't find that, right? Because it seems that you find like once you condition within like age category, then green and non-green like react in the same way. So yeah, how are you thinking about it? And then like is there other cuts maybe of innovation, such as, I don't know, trying to find an estimate for how risky a patent is? Do you find any heterogeneity there?
So when so for the only place where we really looked for risky versus non-risky was in the green non-green split, so not for new technology in general, that we actually found that the overall distribution of innovation looked quite similar. But the broader point, right, is if innovation in young technologies is somehow riskier or for whatever other reason more sensitive to financial constraints, say because the payoffs arise further in the future and therefore the discount rate is more important, all of those features of the world might be true. The point of this paper is even if there is no difference in firms' ability to finance innovation in new technologies or in mature technologies, purely because of the identity of firms that will innovate in the new technologies at the start of a transition, are you going to get that excess sensitivity? So if on top of that, right, there are reasons why firms might find it necessary to cut innovation of new technologies first, for example, because of the things that you just outlined, that's something that you can embed in the model, or it's something that could be part of your mental model. This paper shows you that even in the absence of that, you can get a quantitatively large hit to emerging technologies because of a tightening of financial constraints.
But I guess my question is that true or not? Like, did you
Yeah.
look at it? That
Well, so for
like,
green versus non-green,
do you actually see like this effect like away from risky technologies during financial crisis? Is that like a feature of the data or not?
So for green and versus non-green, our triple diff shows exactly not, right? Because you get very similar. So where that would show up is in our triple diff and diff. You would get much bigger. You would get that this number is much bigger than this number, right? And it is somewhat different. So this might be the fact that green innovation is riskier, but it's certainly not significantly different. Please, Chad.
Yeah, I just want to come back to this point that got raised a little bit and connect it with one of Pablo's points, and ask if you push further. So this point that after the global financial crisis, at the macro level, R&D didn't really decline. On the other hand, as Ufuk discussed earlier, and you noted, that's the one place where it really looks like we lost 10% of GDP permanently. Like at least that's a view. And Ufuk's paper, your paper is equipped to speak to that. So I was just wondering, did you try to see how much you could explain of that type of decline? And then to connect with what Pablo said, the 27 to 28 year point seemed kind of small to me to try to explain that. So I wanted to ask you to maybe address that point.
Right. So the answer to your first question is we didn't try to explain the overall reduction. So qualitatively, I think this might explain part of why you still get this reduction. I think it is important. R&D did fall, right, around the global financial crisis, and broader measures of intangible investments certainly fell. What is a little bit tricky is usually we express R&D in terms of intensity. So we divide it by GDP, and the denominator fell as well, right? So if you look at R&D intensity, it looks totally flat. But if you divide R&D by potential GDP, and that's in most models, the right denominator, there is a hit to GDP. I'm just saying it's about 20%. And to get a flat line of growth for 5 years, in most models, you would have to explain, like, R&D would have to fall 100%, right? And that's certainly not what we saw. But qualitatively, so the only point I wanted to make is that it has to be that the R&D that did fall had to somehow have a lot more weight in overall growth than the R&D that was sustained. The back of the envelopes that calculations that Pablo outlined, I think we should do. I think we should. We've not done it. Yeah.
But to extrapolate on that, like for the decline of startup rate in the US over the past 30 years, that could have a very big impact according to your mechanism or extrapolate version of your mechanism on the emergence of new technologies. Do we see anything?
I think it's a good point. I mean, it has a bunch of effects at the same time, right? Because it's also going to reduce the average extent to which firms are financially constrained. I don't think I have more to contribute beyond that. But I agree with you that young firms seem to do different things, right? As you well know. Bernardo.
Yeah, I was just thinking about this now. I don't know if it makes sense, but your A in the model, which is the productivity of the new relative to the old, is kind of fixed, right? I was thinking that it will be natural that as you have less investment in these new technologies, also this kind of fundamental advantage of the new may decelerate. So maybe that might be a way that the losses can be even bigger than what you are currently measuring.
That's a fair point. So when we quantify the model for green versus non-green innovation, there we actually think of this A as actually the relative costs of producing with polluting technologies, right? So that actually is affected by things like climate policy. It is also probably going to be affected by things like oil prices, right? So in terms of the overall reduction in green patenting, probably the mechanism that we outline isn't the full story, and the fact that oil prices fell probably also encouraged firms to stick with technology with innovation in more polluting technology. In a quantitative experiment, we deliberately hold that fixed, right? Because the question is the mechanism that we have, this self-selection of young firms into emerging technologies, does that have quantitative bites if you put in a well-calibrated financial shock? That's the exercise we're trying to do. But absolutely, the crisis had lots of effects on things like climate policy, right, in Europe, yeah, and on oil prices. Joe?
So I guess one way to read some of this discussion and your paper is that basically the financial crisis is going to lower the quality of R&D. So like Chad was saying, even if R&D is somewhat stable, the quality of it is somehow going to decline. Yeah. Beyond the green, non-green, is there something you've looked at in the data? So for instance, with German firms, you can come up with patent quality proxies, maybe even this KPSS thing, and kind of see how that changes.
So actually, the rigorous theory. So Stina Atesh, for example, has done work on this, right? That the theory would actually suggest that maybe you prioritize the better projects, right? Because on the margin, the stuff you cut are the worst projects. The extent to we've looked at this is we've run regressions weighted by patents, not weighted by patents. All of the plots that I showed you were unweighted, but in the appendix of the paper, we have them weighted. We actually find very little evidence of there being any imbalance there. So it's not something that we emphasize in the paper because we find no evidence that it's the low citation patents that were cut. Yeah.
Anybody wants to have another question? Otherwise, do you want to take a second to say something to Pablo, or do you want to do this at the bar?
I'll do that at the bar, but let me take the second to thank the organizers.
Thanks so much for being here. It's been a really great meeting. Thanks again for the speakers, in particular for the discussants to spend some of their summer to be here. And as we said early on, we hope to see all of you again next year, Thursday, Friday before the EFG. Put it in your calendar right now. Maybe Pete can even tell us if you already have a date for the EFG, so you can all put it in your calendar. Good. Thanks for being here, and see you next year.